Hello, everyone. Welcome to the April 2025 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. I have to start the AMA by being honest and saying that this is difficult to do right now. Most of the Ask Me Anything questions, for perfectly good reasons and for reasons I approve of, are about science and philosophy and recent podcasts we've had and things like that. That's what they should be about. I'm in favor of that. But that's not really what is mostly on my mind or the mind of many other people right now, because the country and the world are falling apart. That is bad. It is hard. It weighs you down in many, many ways. So in the intro here, I just have to get a couple of these things said and on the record, because those are what are actually on my mind right now. As of this actual moment when I'm speaking, the thing that most people chatting to each other on the internet and on news shows and opinion pages and things like that are talking about is the economy, and in particular the tariffs that Donald Trump has put on other countries. And the reason why I want to talk about this a little bit, even though you can find plenty of information about it elsewhere, is I want to drive home, and I don't say this lightly, but I say with complete conviction, the fact that so many people who are in positions of power and responsibility in the United States right now are deeply stupid people. And again, I don't say that lightly, because the fact that I don't agree with you doesn't mean you're a deeply stupid person. I think there's plenty of people out there who I disagree with politically as well as scientifically, whatever, who are smart people. But there is overwhelming evidence that the actual people in charge right now are absolutely stupid people. And I will explain what I mean by that. I won't just claim it out of spite. Think about these tariffs that were just proposed. They are causing the stock market to tank. The stock market is crashing in ways that have not been seen since at least the pandemic, if not much longer. Why is the stock market crashing? Well, because these tariffs that we are putting on other countries, we're basically charging a tax for United States companies to buy things from other countries, okay? That's what a tariff is. And this is terrible for the economy. Not the idea of a tariff. In the right circumstances, used judiciously, tariffs can be perfectly sensible. If a country wants to protect a particular set of workers or industry from being undercut from foreign competition, then you can imagine that there's a place for tariffs. But these are not that. These are broad-based tariffs on everybody, because Donald Trump is a deeply stupid person. And the stock market is crashing because the captains of Wall Street and industrial CEOs and so forth who have supported Donald Trump are deeply stupid people. And what I mean by that is they have been supporting him while listening to Donald Trump say over and over again that he would impose these tariffs. He was not hiding it. It was not hard to figure out. They just didn't believe him. They thought, well, there's no way he would actually do that. He's just playing a game. He's just putting on an act, because nobody could be that stupid to crash the world economy like that. Basically, with tariffs like this, every international transaction becomes more expensive. People are less likely to do those transactions. Prices for everybody go up. Demand for every product goes down, and the economy goes into the tubes. Right? This is perfectly obvious. Every not stupid person knows it, and the Wall Street people are smart enough to know that. They're not smart enough to realize that Donald Trump would do it, despite the fact that it was his favorite thing to talk about doing on the campaign trail, etc. So if they weren't stupid, the stock market would not be crashing. If there's something that is going to happen, and you know it's going to happen, you price it in to the stock market. You buy or sell your stocks preparing for this thing to happen. The fact that the stock market is crashing is not simply a reflection that the economy is going to go into the tubes. It's that people are surprised at the event that is causing the economy to go into the tubes. And that is a reflection of their stupidity, because you could have seen it coming. Plenty of people saw it coming. The tariffs themselves are, you couldn't imagine a weirder, more bizarre story. The proposal, what you're told by the Trump administration, is that they're charging tariffs as retaliation, as reciprocal tariffs, because other countries are putting tariffs on us. that sounds superficially plausible, but then you actually look at the numbers, right? Different countries are being charged different tariffs. Some of it is very characteristic of the fact that the people running the administration are, again, deeply stupid people and also just deeply careless people. They're charging tariffs on islands where there's almost no human beings, and we have at most hundreds of dollars of imports because they really don't know what they're doing. But also this idea of other countries putting tariffs on us doesn't match up with reality. Like some of these countries have no tariffs on us whatsoever. So nevertheless, we're being charged reciprocal tariffs now. What is going on with that? So someone on the internet figured it out. What it actually is not that other countries are have tariffs on us at all. It's that we have a trade deficit with these other countries, which is a completely separate economic concept. The trade deficit is, I give you some money, you give me some goods. Now I have a trade deficit with you because you gave me goods and I gave you money, but we didn't reciprocate. You didn't give me money and I didn't give you an equal number of goods. Anytime I give you more money than you give me, we have a trade deficit. That's not a bad thing in general. I mean, there might be specific cases where it's bad, but the idea that I walk into a store and I want to buy some, laundry detergent and I give them money and they give me goods, that's not a bad idea. And that's called the economy. That's just how things work. But they figured out that when they looked at all the data for the numbers, the percentage of tariff that Trump wants to put on these countries and said, where did these numbers come from? They figured out basically they just took the trade deficit that we have with these other countries, divided by the total number of imports, and then divided by 2 because it's a random number that they chose to divide by 2. So in other words, the amount that they're claiming other countries are tariffing us by has zero to do with the existence of tariffs. Even there's a non-zero number there, even if there's no tariffs whatsoever. And you think that that's just too stupid to actually be true, but the actual U.S. trade representative went on the internet and said, no, that's not true. We have a formula. And he gives this formula, and I have to laugh. Why am I laughing? Because these people are deeply stupid. And you either laugh or cry. Those are the only two choices. So he gives a formula for this percentage, and it looks very much like the trade deficit. The trade deficit is, the amount of money we give them versus the amount of money they send back versus the total number divided by the total number of imports. But then there's 2 extra numbers in the denominator. They have a very simple formula. It's just a fraction. It's not that complicated mathematically. But they put 2 extra factors in the denominator, epsilon and phi. Ooh, Greek letters. Clearly very, very sophisticated mathematics going on here. And you look up what they are, and I actually looked it up for you. I will tell you what they are. Epsilon represents the elasticity of imports with respect to import prices. And phi is the pass-through from tariffs to import prices. Ooh, very, very sophisticated, right? Who knows what those words mean except for professional economists who clearly know what's going on. But then you dig a little deeper into what epsilon and phi are, and they said that for purposes of doing the calculation, they set epsilon equal to 4 and phi equal to 1/4. So when you multiply epsilon times phi, you get 1, and those factors have nothing to do with the calculation, and the percentage of reciprocal tariffs is exactly coming from the trade deficit. Nothing to do with tariffs whatsoever because these people are very, very stupid people. So these are the people who run us right now, and it's a combination of people who don't know what they're doing being supported by people who thought they weren't stupid enough to do what they're doing, and that breaks my heart. But it's not the thing that is mostly breaking my heart. I'm mentioning that just because, or primarily because, that's what's on most people's minds right now. And it is going to be disastrous. It's going to be disastrous for rich people, for poor people, for people who need any retirement savings, anything like that. It's just going to be a disaster for people who want to buy any good that is made outside the United States, and also many goods that are made inside the United States. If you like electronics or T-shirts or most fruits and vegetables, you're out of luck. Sorry about that. The thing that is on my mind is I was just at Santa Fe Institute. I was just doing one of my biannual visits there. And I was talking to Sam Bowles, previous Mindscape guest, and also Katrine Schmeltz, who is a researcher at Santa Fe. And she's also an economist. She's working with Sam. They're working together on, they're economists, but broadly construed. So, in fact, their current project is on actually authoritarianism and how it reflects people's personal attitudes in both ways. Like if you live under an authoritarian regime, does it make you more or less amenable to being authoritarian even in your life, right? So it's a very kind of interesting project. And Katrine is from East Germany, where she grew up. It was in communist East Germany, but you could see West Germany across the border there. And so they can do a comparative study because they're all Germans, but some of them have lived through authoritarianism. Others just grew up in a liberal democracy. Anyway, so Katrine and Sam found out that I had this project bubbling in the background about the physics of democracy. So they said, well, let's talk about that. Let's have a little seminar. Let's do an SFI seminar on democracy and dynamics and physics and things like that. So we did that. But the reason I'm mentioning it is because the day we did it was in that morning, people on the internet saw this video of the Turkish student Rümeysa Öztürk. Sorry if I'm not pronouncing her name correctly. So she was a student at Tufts University who was arrested on the streets by agents from ICE, the Immigration and Custom Enforcement Agency here in the United States. And I don't know if you've seen the video on the internet. It is completely chilling. Like, you can't watch this video without some fear running through you. This is Somerville, Massachusetts, where she was arrested. I say arrested, but it's not like these were officers in uniform who picked her up. These were plainclothes people wearing hoodies, and some of them have masks. I know that in certain corners of the world right now, the idea that you're wearing a mask automatically characterizes you as a terrorist sympathizer. But these people wearing masks as ICE agents, and they picked her up and they put her in an unmarked vehicle and drove her away and disappeared her for a little while. We have since figured out where she is, Rümeysa Öztürk. And why? Well, she was a Turkish citizen, but she was here in the United States on a perfectly legal visa. The government revoked her visa, her student visa. They didn't tell her that her visa had been revoked. They just picked her up and put her in a van. And she's a student. Why? Why is she doing this? Why are they doing this to her? Well, we don't know. This is part of the danger and scary aspect of living in a world where democratic norms are failing, that the government can just take you without any due process whatsoever. And many Trump administration officials are on the record as saying, well, we shouldn't give due process to people who we think are terrorists. Of course, the problem with that is, without giving them due process, we don't know whether they are terrorists or not. That is the purpose of due process, to actually have a process through which we can make sure that you're not being unjustly accused. As far as anyone can tell, the only thing that the student Öztürk did is co-sign an editorial a year ago in the student newspaper calling for, some disagreeing with some statements that have been made by the president of Tufts University. What the government says is that she was arrested due to, they say it now, they didn't say it at the time. At the time, they give no reason at all. But since then, the Department of Homeland Security has stated that she was arrested due to support of Hamas, the terrorist Gazan organization. That's it. Support of Hamas. Like, what does that mean? Support. Just a feeling in your heart? Can we be arrested and deported now for feelings here in the United States? Elsewhere, Donald Trump has an executive order saying that they would revoke the visas of students he characterized as Hamas sympathizers. So the existence of sympathy is apparently enough to have your visa revoked. If you look at the op-ed that was signed by Öztürk and others, there's no mention of Hamas. There's no support of Hamas or anything like that. It's not about that. It's about the Tufts University's relationship to students at Tufts protesting, and also to the state of Israel, and you're welcome to disagree with her views, but they're being entirely mischaracterized for the sake of disappearing somebody. And It's scary. It's scary to people at universities. It's scary to people who travel. I'm trying to organize a conference where we have people coming in from other countries. Who knows what can happen? And you say, well, this person wasn't a United States citizen. It doesn't matter if they're a United States citizen or not. For one thing, she was here on a visa. For another thing, even if you're a United States citizen, if the government says we can do things to you, disappear you to locations elsewhere without due process, they can revoke your citizenship. And then you're not a citizen anymore, right? They think that they have that right. It is truly stomach churning to me. And I know that many people listening right here don't want to hear this. They want to hear about quantum mechanics and whatever. But this is what is on my mind right now. The fact that this is where we've come to, where we've stooped to. I mean, it gets worse, of course, right? There's other people have been disappeared to this terrorist detention center in El Salvador, some admittedly by accident, right? The government admitted that they made a mistake and picked up the wrong person. But once they're there, deported to El Salvador, the government says, well, we don't have to bring them back because now they're not in our jurisdiction anymore. That is how low we are right now. It's extremely scary to me and to other people. So I have no solutions for this other than to, protest, make your voices heard. Various of us faculty at Johns Hopkins are talking about what we can do more substantively, but I don't have anything to talk about that right now. But we're thinking about it and looking into it. We need to do it. We need to group together. Universities, law firms apparently have to group together also, certainly state governments. I have re-upped my memberships in the American Association of University Professors and in Penn America and other places like that. We need some opposition to this degradation of democratic norms. That's what's on my mind. How about you out there, everybody? It feels weird to shift gears like this, but I'm going to say thanks to all of the Patreon supporters of Mindscape, who are the ones who send in support. They get ad-free versions of the podcast, and they also get to ask the questions for the AMAs. So, of course, needless to say, you could be an AMA supporter of Mindscape if you wanted to. Go to patreon.com/Sean M. Carroll and ask the questions. And, sometimes we get questions in the AMAs about these issues, politics and the state of the world and so forth. But mostly they're not about that, and I think that's entirely 100% appropriate. I think both are entirely 100% appropriate. We don't want most questions to be like that. We want Mindscape to be mostly an escape from these kinds of things and sort of an effort to keep up the other parts of our lives going, keep up the intellectual curiosity and the thinking about the world. But we can do that while still acknowledging that we live in the world. And the world is sometimes a scary, messy place, and we got to figure out what to do about that. So with that, let's go. Edward Crump says, when I hear professionals discuss human space travel, almost nobody includes the fact that we will never even get to Alpha Centauri, only 4 light years away. That's thousands of years away with our best technology. What is your thought? My thought is to completely disagree with that. I think there's no reason whatsoever to think that we can't get to Alpha Centauri. As you say, it is thousands of years away with our best technology. That's a bit of an exaggeration in the positive sense, because right now our best technology can't get us to Alpha Centauri. You can't get human beings to Alpha Centauri. But certainly technology that is completely foreseeable and anticipatable could get us to Alpha Centauri, and it would take thousands of years. But number one, obviously, if we wait 1,000 years, then our technology will be better. The weird thing about imagining launching a spacecraft to Alpha Centauri is that you just wait a century or two and make another spacecraft and you'll pass it along the way, right? So I think it's completely wrong to think that our best technology right now is relevant to the question of going to Alpha Centauri. The other thing is that, thousands of years is not that big a deal. Thousands of years is not that long. Again, we'll get better technology and we will either be able to put people into cryogenic suspension and have them sleep through the voyage, or just increase their lifespans to a couple 100,000 years. No problem whatsoever. I think you can't just take the current situation situation and extrapolate it blindly. So that's well past my own personal lifetime, but I think that if you're thinking about the far future, going to Alpha Centauri doesn't seem difficult whatsoever. Mark Slight says, at some point you mentioned a mug can quantum tunnel through a table. Does that mean there are also quantum effects when putting a mug on a table without tunneling occurring? Is there some measurement taking place upon mug touchdown? Well, let's talk a little bit about, there's different levels of answer here. So let me give you the most basic one first. Of course, there are quantum effects when you put a mug on a table, because there are quantum effects that keep matter stable. The fact that the table is solid is 100% a quantum effect. It is traceable to the fact that electrons take up space in atoms, and that's because of the Pauli exclusion principle, because electrons are fermions, which is a fundamentally quantum mechanical thing, okay? So quantum mechanics is there, even in the everyday physics of solid and liquid materials and things like that. The question about measurement is a little bit different. Of course, in some sense, yes, it's a measurement. I measure the fact that the table is there. It's not really what we usually think of as a quantum measurement, because before putting the mug down, the table was not in a superposition of different possibilities, at least not noticeably in a superposition. Usually, the sort of relevant kind of quantum measurement that we talk about is one where there's a quantum system that is in a superposition of different possibilities, and we're measuring which possibility it's in, right? Spin up or spin down or whatever. That's the quantum measurement, as opposed to an ordinary classical measurement. When you put the mug on the table, you're doing a measurement. There's the table. You're finding it. You can hear the clink of the mug. Oh, yes, there was a table there. That's good. But it's completely compatible with the rules of classical physics. You don't need quantum mechanics to talk about that. Anonymous says, I was listening to the Something Deeply Hidden audiobook, and while I enjoyed it, I couldn't help but miss the more casual Sean Carroll voice that is used when you're reading AMA questions. I'm wondering if the engineers for that recording session encourage you to use a more performance-sounding cadence, or if you just did that because that's what you're used to hearing in other audiobooks. Neither one, really. It's just that an audiobook is a weird thing. An audiobook is taking a set of words that were meant to be read and reading them out loud. But written speech and spoken speech are two different things in all sorts of ways. You construct the sentences differently. You put emphases in different places. So I'm just reading a written text. That's all it is. Even these AMA questions are not, meant to be parts of a book, right? People write them in a pretty casual way, so I can read them in a pretty casual way. And it's nothing pro or con about reading things out loud versus reading them on the page. It's just different. And the fact that they're different is completely appropriate. It's not like one is right and one is wrong. In a book, look, those books are all based on videos that I did, right? So I first did them as more or less extemporaneous videos, and then I turned them into books. And it's much harder than I anticipated to turn them into books. I should have known. Maybe I'm not that smart either. But exactly because the written word, and especially in the form of an entire book, is a different beast than the spoken word. And there are advantages to that, because in writing you can be much more precise, but you can also be much more sort of back and forth. You read a book and it's linear, of course. You read one page, then another. But you can skip back and you can skip forward, right? Very easily. Books have a very short access time to different sets of pages, and you can look at what that equation was, and then you can, remember what that figure said, and even read a whole paragraph again, in a way that the linearity of the spoken word is much more in your face. It's much harder to go back and forth in an audio book format than it is in a written book format. So the written book sort of imagines that you have that ability to go back and forth, and therefore the discussion can be much more layered, nuanced, imagining, I guess, cumulative is the important idea here. You're really imagining that you have the ability to go back and remember what was said before, and that affects deeply how the book is written. So I don't think it's better or worse or different. I think, or unintentional. I think that it is intentional that audiobooks are going to sound different than ordinary casual speech. Fabian Rostelin says, for branches of the universe that split off very close to the Big Bang, could they be different in some fundamental ways like constants in physical laws? They could be. Longtime listeners will know that that is always the answer here. Let me say two things. And I think I've answered this one before, but maybe not. I don't remember, so that's why I'm answering it again. The traditional standard way of thinking about Everettian quantum mechanics says that the laws of physics in the different branches of the wave function are exactly the same. If I measure the spin of a particle and it's spin up or spin down, I don't change the laws of physics by doing that measurement. But Fabian's question specifically goes back to the early universe and says, early on branches, et cetera, et cetera. There, the possibilities are slightly different. I can imagine that there are differences in physical laws because I think that the physical laws depend on what parts of the wave function of the universe are sort of participating in the branch that you are on. But I don't think that anyone has actually worked that out carefully. It is something that I would like to do. I've started doing it a couple times. I've never quite finished, but hopefully that'll be a paper that I write someday. Matthew Willey says, Thomas Nagel highlighted the difference we need to travel to understand what it is like to be a bat. I have trouble imagining what it is like to be my daughter. She has severe cognitive impairments and, for example, at 17 years of age, has no alphabet or number understanding. It's been my privilege to watch her develop her own workarounds, often using tech prostheses, such as text-to-speech, to level the playing field. She has a burgeoning scientific interest in the world and photographs which she finds difficult to describe in words. Do you see the growing acceptance of neurodiversity as something that can inform our understanding of ourselves? Yeah, I absolutely do. And in fact, I think it's part of a bigger thing. I mean, not to be too grandiose about it, but in its best moments, the idea of the liberal social order includes the idea of an expanding circle. Peter Singer, the philosopher, talks about the expanding circle of care. He's an animal rights activist, among other things, so he wants to care about the feelings of animals as well as human beings, which is fine. But even more directly than that, we think of more and more people as human, right? We give the right to vote to former slaves, to women, and so forth. And I think that that's there's a political aspect to that, but it's also just a general tendency that we get better and better at seeing the humanity in people who are not like ourselves. Clearly, this is not a one-way street. It is not monotonic. There are pluses and minuses, ups and downs, the whole bit. But I think it is a general tendency. And in particular, the idea of neurodiversity, the idea that there are people who are differently organized than us, people who think differently than us. And it is not simply a matter of them being worse at thinking than us. Maybe they're better in some ways. Maybe they're worse in other ways. Maybe they are worse. That's possible. I'm not discounting that possibility. But there's also maybe something that they're better at. And that is something that we can appreciate and really value in a world where we've advanced a little bit from where we were 2,000 or 10,000 years ago. And I think that the growing understanding, we've had people here on the podcast who are autistic or, have different sexual orientations or whatever. And I think that as a culture, we can overall, again, there's ups and downs, but we can get better at appreciating and allowing for that. And therefore learning from it. To get to your actual question, it can teach us. It can teach us ways of appreciating different ways of thinking and things like that. I mean, there's a bit of retrenchment, I know, in the contemporary moment. People are sort of fighting against diversity in various ways. By the way, if you follow me on Blue Sky, I posted something because I work right next to the Space Telescope Science Institute. In my office at Johns Hopkins is across the street from that. Hopkins operates the Space Telescope Science Institute, so I often have lunch at Space Telescope. And a couple months ago, I was there, and I noticed that in the lobby of the Space Telescope Science Institute, there's a sign, and it says, the Space Telescope Science Institute promotes an inclusive, equitable workplace and cultivates a diverse, engaged workforce. And I read that sign, it goes like, that's not surviving. It's that celebration of diversity and equity doesn't seem like it's going to last very long in the current environment. And indeed, when I went there for lunch a couple days ago, the sign was gone. So clearly our progress in appreciating diverse perspectives is not always increasing. Sometimes it goes down, but I think overall it is increasing. I think overall it is a good thing. Peter Krausp says, in Quantum Fields Chapter 10 on phases, you used the phrase phases of gauge theories. Maybe it's a language problem on my side as a non-native speaker, but what is a phase of a theory? In the context of quantum field theory, it would seem to make sense to talk about the phase of a quantum field configuration or similar, while a phase of a theory could refer to how a theory evolved in the history of physics, but I'm sure that's not what you meant. Perfectly fair question, Peter. I'm sorry that I didn't do a better job of explaining that because the word phases has a family resemblance to the word emergence in the sense that scientists and philosophers use it in a time-independent sense, even though the sort of more casual, everyday, on the street meaning, as something that evolves with time. You emerge like a chick emerge from its shell, right, of the egg. Likewise, things pass through phases in the real world, and I think that that's how people think of things. The standard example of phases is water. You have liquid water, you have solid water, which is ice, you have water vapor, and obviously we're very familiar with changing from one phase to another. So again, it seems like a dynamical thing. In quantum field theory, rather than thinking of phases as a function of temperature or time, we think of phases as a function of the parameters in the theory, or even just the dynamics of the theory. So it's very close but slightly different in the meaning that way. So in that chapter 10, for example, you can think of the Coulomb phase or the confining phase or the Higgs phase. These are the three famous phases that a gauge theory can be in. The Coulomb phase is when the gauge bosons are massless and can go to infinity. So you have gravity, you have electromagnetism, both of which have long-range inverse square force laws. Those are in the Coulomb phase. Coulomb's law is the electromagnetic inverse square law. The confining phase is when the particles, the gauge bosons, are massless, but they're also strongly interacting with each other, so they don't escape from the bound states that they're in strongly interacting particles, in hadronic particles, either baryons or mesons. Whereas the Higgs phase is the one where the gauge bosons are massive because there's been spontaneous symmetry breaking and the force becomes short range. So none of these are examples. Well, strictly speaking, there are changes of phase over time. In the early universe, we believe that when the temperature was very high, the weak interactions were in the Coulomb phase. They were not Higgsed, as we say. The symmetry was not yet broken. And there's a moment, the electroweak phase transition, where you go from the Higgs field having zero expectation value to the Higgs field having a non-zero expectation value. But at zero temperature in the late universe, the field simply is in the Higgs phase, and that's a way of saying that all of the dynamics and the parameters and the field content of the model team up to give the field certain behaviors. So you should just think about it as a characterization of how the fields behave, rather than as something that comes and goes as a function of time. James Kirkland asks a priority question. Remember that every Patreon supporter once in their lifetime gets to ask a question that I will try my best to answer, as long as they label it a priority question. We've been around long enough that a couple times this month people said, I'm asking my priority question, but I forget what I've already asked one. Because we've been doing it for a few years now. I just want to reiterate, it is in your hands to remember whether you have asked a priority question before. I'm not keeping track of that. That's work. So I'm trusting you folks not to abuse the privilege. And James says, in your recent solo episode, Does Time Exist? You went over the standard argument for Boltzmann brains, and in listening, I realized a possible problem with the argument I hadn't considered before. The problem was this: in choosing a time to consider the observable universe as our frame, I'm not quite sure what that means, but I'll keep going. We choose an observable universe different to if we had chosen some period of time previously or after, due to the contraction of what is observable due to expansion. In this sense, the Hamiltonian that is actually appropriate to ever use for a specific region of space-time is constantly shrinking. You can't reasonably use relativity to choose your Hamiltonian via a light cone to analyze and then ignore the change in that light cone over time. Not sure if I missed something or if this doesn't matter, but it seems on the face of it that this leak makes the process nonlinear. Am I missing something, or is this in some way analogous to the problem you described with your PhD students? I will confess, James, I do not understand the point you're making. I have no idea what it means to say that the Hamiltonian that it is appropriate to use for a specific region of space-time is constantly shrinking. I'm going to try to translate it into words that I do understand, and that may or may not be what you had in mind, but I'll do my best. The Hamiltonian I think of as a set of equations, right? The Hamiltonian is, technically, classically, it's a function on phase space. Quantum mechanically, it's an operator on Hilbert space, but it's a fixed thing. It's not changing with time for the most part. So for it to be shrinking, I'm not sure what that means. Maybe what you mean, probably what you mean, is the actual matter content of the universe changes because some particles, etc., go away. They go outside our horizons in a de Sitter universe. And that's certainly true, and that's a big part of what we call the cosmic no-hair theorem, the idea that in a universe with a positive cosmological constant, eventually the universe empties out and becomes asymptotes to what we call de Sitter space, an empty universe with a positive cosmological constant. So I would say the Hamiltonian is the same, but the matter content is actually different. Now, this by itself doesn't say that Boltzmann brains can or cannot pop into existence, but it's closely related to the fact that if you are in a world where the laws of physics allow you to settle down to a static vacuum state, then Boltzmann brains do not pop into existence. The sense is that if the universe were a box, with fixed boundaries and it couldn't expand or contract, then the number of matter degrees of freedom in some sense in the box stays constant over time, and the box can't settle down. The fact that the laws of physics just move things forward in time say that you can never sort of hit a barrier and stop at any one point, okay? So there's a constant churning if the universe were a box. But the universe is not a box. The universe is expanding. And due to that expansion, the set of things within our observable patch of universe that are moving around can decrease over time. And that gives the universe the ability to settle down, at least locally in some region. So in that sense, yes, it is exactly that process that lets you potentially wriggle out of the Boltzmann brain problem in a universe that can settle down. Nick J says, let's say I measure the temperature of a cup of water. The act of sticking in the thermometer will disturb the water molecules, leading to a slightly higher temperature than if I had left the water alone. The measurement has changed the system with potential dramatic effects, e.g. a phase transition. What makes a quantum measurement so different from a classical measurement like the one outlined above? Easy. The classical measurement you just did badly. If you want to measure the classical system carefully, you can do that. There are ways to make your intervention in the system while measuring its temperature or whatever as small as you like. There is a limit in which you don't change the system at all. Quantum mechanics is very, very different than that. If you have a spin that is in a superposition of 1/2 spin up and 1/2 spin down, and you measure the spin, then no matter how delicately you do it, the quantum state is going to change dramatically. That is an entirely new quantum mechanical thing. You can get a very different answer than what the state was before you did the answer, no matter how carefully you do your measurement. That is a truly new thing in quantum mechanics. DMI says, could you enlighten me on where my assumptions or reasoning go wrong here? Fermion wave functions must have zero overlap. The amplitude for one fermion must be exactly zero wherever the amplitude of another fermion is non-zero. The Fourier transform of a non-zero function that is zero in a set with positive measure must have arbitrarily high frequency components, therefore Hilbert space is infinite dimensional. But too much energy would collapse into a black hole, so it can't be infinite dimensional. Yes, I can enlighten you on where your assumptions go wrong. It is in step 1. The statement that fermion wave functions must have zero overlap. That is clearly not true. You can just look at the orbitals of electrons in atoms. They have plenty of overlap with each other. I know why you're saying this. It's a reasonable thing to think, but it's not quite true. The true thing is that fermion wave functions must be orthogonal to each other, right? They must be perpendicular to each other in the inner product on Hilbert space. As vectors, they must be perpendicular, okay, orthogonal. But that doesn't mean that at every point in space, you can't have two different fermion wave functions that are both non-zero. Think about, vastly simplify your life. Think about a two-dimensional plane, think about xy axes, and think about two vectors from the origin that are orthogonal to each other, okay? If the vectors are exactly in the x direction and the y direction, they're orthogonal to each other and they have no overlap. Overlap here meaning, do they both have a non-zero x component or y component, right? If they are exactly pointing along the x and y axes, then no, they have no overlap. But if I rotate them just a little bit, keeping the two vectors perpendicular to each other. So let's say that one is 45 degrees between the x and y axis, and the other one is pointing in minus in the x direction and still plus in the y direction, 45 degrees between the minus x and the plus y axis, okay? Now they have overlap, in the sense that both of those vectors have non-zero x components and y components. But when you multiply those x and y components, you get two non-zero numbers that cancel because one of them is equal and opposite to the other one. That's exactly analogous to the fermion wave functions in space. The value of the wave function at a point in space is precisely the component of this infinite dimensional vector in the position basis for that wave function. So you're absolutely welcome to have two fermions that have non-zero values at the same location in space, as long as the sum of the products of all the non-zero values at every position in space adds up to zero. That is to say, as long as the overall inner product is zero. And that's completely possible, happens all the time. David Sotolongo says, in a Thanksgiving 2022 post on your website, you discuss various voting systems and indicate that some are better than others. For example, noting that the U.S. voting procedures are laughably primitive, which I agree with. I had a few questions related to this. First, do you have a philosophy for determining what might constitute the best or most legitimate type of electoral system, such as choosing the most utilitarian electoral system or a belief that the system should be chosen from behind a Rawlsian veil of ignorance? Remember, folks, people are getting a little sloppy here, but you're only allowed to ask one question in the AMAs. So I know you said first, but this is going to be the only question. I don't have a well thought out philosophy of determining what might be the most legitimate electoral system. I think that, there's a situation where certain systems are definitely better than others, without necessarily having a criterion or an optimization procedure for finding the perfect system. Maybe I could come up with one, but I don't think it would be utilitarian. I think that, there's one of the nice things about the U.S. system is that it at least tried to protect some of the rights of the people who were losing elections, right? I mean, we've taken that a little bit too far in some ways, but that is absolutely a good thing. So I don't think it's about choosing from a Rawlsian veil of ignorance, although maybe, so I don't think so because I haven't thought of it, but maybe something like that would work. Rawls's point about the veil of ignorance is that you would try to choose, if you were behind the veil of ignorance, so you didn't know how successful you were, you would try to protect yourself from being really, really badly off, okay? Other people disagree with that, and they would say, no, I'm willing to risk a little bit. Rawls had some arguments, and you can disagree with his arguments. But in that perspective, if you follow Rawls's reasoning, you would probably try to come up with a voting system that minimized the unhappiness of the least happy people with the outcomes of the elections. There was, I think I referenced in that 2022 blog post, but there was a study that tried to actually propose a criterion, a metric for the goodness of different voting systems, and it was called Bayesian regret. I don't remember, I have no idea why it's called Bayesian regret. I don't remember who did it, but if you look up that blog post, my blog posts only come in like one or two a year now, so I had the podcast instead, so it's not hard to find things on the blog these days, but it's still there, preposterousuniverse.com/blog. And I think there's a link to the people who did that particular study. So I think that it's possible to think about that carefully. I just personally have not thought of it carefully. Humberto Nani says, I really like the explanation about how new physics won't change everyday life. Could the observer being part of the fundamental ontology be ruled out in a similar way, like it won't be needed regardless of which interpretation of quantum mechanics turns out to be the correct one? Well, I think that spiritually there's a relationship there, but it is far less cut and dried. The argument that new physics won't change everyday life benefits from the fact that we really understand effective quantum field theories, right? And this argument starts from assuming that the world runs according to the rules of effective quantum field theories. And then given that assumption, you can really show that, new physics, high energy phenomena, et cetera, decouple from the low energy infrared physics that we see on the everyday basis. And I always have to say, people don't pay attention, but I always say, of course, maybe there's something wrong with effective quantum field theories. Good. Then you have to tell me exactly what's wrong with it. But the argument about the observer being part of the fundamental ontology does not live within some well-defined theoretical framework, right? I mean, that's the problem with it. What do you mean by that? I don't mean you specifically, but what do people mean by that when they say that? Observers are big, complicated things. I mean, this is one of the problems to me with either epistemic approaches to quantum mechanics or just idealism more generally as a philosophy of ontology. Putting consciousness or agents first has the huge downside that we don't have a very well thought out description of what an agent or a conscious creature is. We have a really mathematically rigorous description of what a quantum field is. Our physics is really, really good. Our ability to talk about agents is not so good. So it's kind of vague and loosey-goosey, and the people who want to advocate for this are able to wriggle out of all sorts of problems. So, maybe you could absolutely make the argument that believing that perspective, that the observer is part of the fundamental ontology, makes no difference to any prediction you ever make. But it's kind of like arguing against the existence of God. People are going to have different conceptions of what God means or what the agent or the conscious creature is, and I'm not going to say that they wouldn't be able to wriggle out of any kind of argument you put up along those lines. Earth to Dan says, in Something Deeply Hidden, you explain that the pop science mental model of particles in the vacuum constantly being created and destroyed is not literally true, but rather a particle-centric way to explain that the vacuum energy is non-zero, where there exists only a probability of how the energy might be quantized. If I got that right, then my question is, what is the non-particle explanation of the Casimir effect, where a gap between materials too small to host spontaneous particle pairs creates a vacuum pressure? I think that you almost got it right, but not exactly right. The overall thing is that what exists is the quantum state, and not particles or fields or anything like that. It's the quantum state. Now, it is convenient to talk about the quantum state as being a quantum state of fields, but that's going to break down at some point. That's okay. For these purposes, that's perfectly fine. In a subset of interesting circumstances, it is okay to talk about the fields as representing particles. Inside a proton, it's really not very convenient to do that, but for an electron going through a bubble chamber and leaving a track, then that makes perfect sense. For individual atoms, talking about particles, that's perfectly fine. You just have to keep in mind that it only makes sense in a particular restricted set of circumstances. Okay, so the point is, for the vacuum energy or for the Casimir effect, it's much better to talk about fields than particles. There's not an excitation of the field. You're basically in empty space for the vacuum, literally. And the Casimir effect, for those of you who don't know, is the same as the vacuum, so it's empty space. But you imagine you have boundary conditions, for example, from two parallel, perfectly conducting plates. What does perfectly conducting mean, or why do we care? Well, that means that something like the electron field will go to zero at the location of the plates. So for those of you who've read quanta and fields or other explanations I've given to you about the discreteness that quantum mechanics imposes because of boundary conditions, it's much like the modes of a plucked string on a guitar or a violin, where you hold down the edges of the string, and then you have certain vibrations with integer numbers of wavelengths or half integer numbers of wavelengths in between. The Casimir effect says if I have these not charged, but conducting parallel plates, that provides a boundary condition for the vibrating quantum fields inside. And the fields are, again, not literally vibrating, but rather there's a quantum state of them that is a superposition of all the possible vibrations. And the possible vibrations are limited by these boundary conditions. You can get some vibrations, you don't get others. And what you can do a calculation to show is that the energy density of the quantum fields inside the plates depends on those boundary conditions, which makes perfect sense. You have some allowed vibrations, you don't have others, that's going to change the energy that you have inside. And roughly I forget how it goes, it depends on whether you have fermions or bosons and things like that, but I believe it's an attractive force in the real world for electron fields inside two parallel plates. And therefore, there's a Casimir effect, which is that there is a force that acts on the plates and pulls them together. That's because a force is a derivative of an energy. And if you have lower and lower energy as the plates come closer together, that's essentially a force that is pulling them together. That is the non-particle explanation of the Casimir effect. I don't even know what the particle explanation of the Casimir effect would be. That seems very strange to me. You really need to talk about the fields and their wavelengths to get an explanation of the Casimir effect. AJ says, I just finished your great episode with Christopher Cook, and I believe you said you haven't experienced a transcendental or alternate state of consciousness, psychedelically induced or otherwise. Is that right, and have you considered it even as a way to inform your views of consciousness or even just for fun? I have. I think I've said before, I did LSD once. That is the closest I have to a psychedelically induced altered state of consciousness. It did not really inform my views on consciousness. I would go so far as to say I truly do not understand how it could inform my view on consciousness. If you know that you're doing things chemically to your brain that changes how neurons fire and therefore the conscious impressions you have of what's happening, what is that supposed to teach you? I know that's going to happen. It happens. What did I learn? Certainly, I don't know of any way in which that would sort of give me a more expansive or accurate view on consciousness. Maybe it could. I'm open to the possibility. No one has ever explained to me how that could possibly work logically, and it certainly didn't happen for me. Matt Grinder says, is it possible that the randomness and uncertainty of quantum collapse is due to the vacuum energy? Is this a bad question somehow? No, it's not a bad question, but no, like my answers to questions beginning, is it possible, is always yes. But when I say that, it's because people usually are asking questions about, is it possible that this theory that I just came up with is true? And that's always possible, even if it's very unlikely. But the vacuum energy doesn't really have anything to do with the randomness or uncertainty of quantum collapse as we understand it. There are various explanations for the randomness and uncertainty of quantum collapse. It depends on your deep ontology of quantum mechanics. Is it many worlds? Is it Bohm? Is it spontaneous collapse? All of those are possibilities. But the thing is that vacuum energy is just a constant. That's the thing about being in the vacuum. It's the same energy everywhere. So it's not doing anything. It's not giving you any differential influence on what happens in one place or one event versus another one. The only thing that vacuum energy does, as far as we know, is it has energy, and therefore it acts as a source for gravity, and therefore it affects the metric, the curvature, the geometry of space-time, according to Einstein's general theory of relativity. The most obvious way that shows up is that it makes the universe accelerate. But in principle, even here in the solar system, there is vacuum energy, and it slightly affects the Schwarzschild metric. The metric should be closer to Schwarzschild de Sitter rather than just Schwarzschild all by itself. And therefore, things like the precession of Mercury are affected by the existence of vacuum energy. It just turns out that numerically that effect is so incredibly small you will never, ever, ever see it. But because the vacuum energy is the same everywhere, doing the same thing at all places and all times, by definition of being the vacuum energy, I don't see how it could be involved with quantum collapse due to measurements. Matthew Wright says, as someone with a mathematics background, I was surprised when I learned that representation theory has applications to particle physics, but I've never quite understood how it applies and how particles correspond to irreducible representations of groups. Do you have a good way of explaining or understanding the connection between the two? I don't know if I have a good way. I can just explain, I guess, what I take to be the conventional way. First, for those of you who are not mathematicians, representation theory is an important part of group theory and becomes super duper important for particle physicists. The idea is the following: a group of, to a physicist, symmetry transformations. To a mathematician, a group is just a set of objects with certain relationships and a certain product structure. I can take two objects, I can multiply them, and I can get an answer, and there's an inverse and things like that. That's what makes a group. So rotations are a group because I can do a rotation in one way and then in another way, and I get a third rotation on the net. Or the numbers, the real numbers under addition are a group because I can take two numbers and I can add them, and there's an inverse. Real numbers under multiplication are not a group because there's not always an inverse, right? I can multiply by 0, but I cannot divide by 0. So the real numbers under multiplication are not a group. That's what a group is to mathematicians. To physicists, the relevant groups are symmetry groups. So rather than just abstract objects, we think about transformations on systems. So rotations. Translations are moving a system by some amount, and I can move it by one amount, then move it by another amount. That adds up to having moved it by a third amount, so that makes a group. All of the stuff that we do, as you know if you've read Quanta and Fields, in particle physics with SU3, SU2, U1, these are all groups of symmetry transformations on the fundamental fields. But there's also the idea of the representations of the group, which is different kind of, I want to say physical systems. There's more mathy way of describing it, but let's try to be physicists for the moment. Different physical systems will change in different ways under the action of a group. A group needs this multiplication structure, and it also needs an identity or an inverse. So let's think about objects in the two-dimensional plane, right? How do they change when I do a rotation in 2 dimensions? Well, if it's a circle or a dot and I rotate around the location of the dot, it doesn't change at all, right? I can still think about the effects of rotations, but the effects of rotations are pretty trivial. The dot never moves if I rotate around the dot. Now, if I have a vector, a little arrow that begins at the dot and then has a straight line with a little arrow head on it, okay, that does change under rotations. I can rotate it around, and if I rotate it around by 365 degrees or 2 pi radians, it comes back to where it starts. So that is the identity transformation, rotating by 365 degrees. But what if I have a double-sided arrow? What if I have an arrow that has 2 arrowheads and the middle of the arrow is where the dot is and I rotate it around that, okay? That still changes when I do a rotation, but it has the property that it comes back to its original starting point after only 180 degrees, not after 360 degrees. So I'm imagining that this is an abstract arrow. Like, I don't even know the stuff of which the arrow is made. All I know is that it points in these 2 directions. And if I rotate it by 180 degrees, now it's back to exactly the configuration, looks like the configuration that it started in. So mathematically, I say that the dot, the ordinary vector, and the double-sided vector are 3 different representations of the group of rotations in the 2-dimensional plane. 3 different ways that a physical system can sensibly change when I do those representations, when I do those transformations, I should say, sorry. So the way that it actually comes up in particle physics, I'm trying to come up with a good example that is not trivial. But, you know, you have these groups of symmetries, SU2, SU3, etc. And also you have the group of space-time symmetries, right? Rotations, like we were just talking about. And indeed, forget about SU2 and SU3 because those generally just have the simplest representations. But the rotations in space, given that you're working with quantum fields, they can have various different representations. They can be things that come back to where they started after a 360-degree rotation, or things that come back to where they started under a 180-degree rotation, okay? Or they can be things that come back to where they started under 2 rotations all the way around, which makes 720 degrees. All of these are realistic possibilities in the mathematical theory of representations of the rotation group. And it turns out that in quantum field theory, these are all actually instantiated by real quantum fields that actually do change in that way. So what physicists tend to say is that, well, I should add one more fact there, of course. These representations of the field are classified by what we call the spin of the underlying quantum field. A spin 1 quantum field comes back under a 360-degree rotation. A spin 2 quantum field goes back to where it started under 180 degrees. Spin 1/2 comes back to where it started under 720 degrees. Spin 0 is the same under any rotation, okay? So all of these things that we've been talking about are actually appearing in the zoo of quantum fields and their associated particles. So I was starting to say that physicists tend to sometimes say that's why there are particles with different kinds of spin, because there are different representations of the rotations. It seems like they know the answer. They know that in the real world there are these different particles and fields, and therefore they think they've come up with an explanation of it. To be a little more careful, I would prefer to say it's the existence of these different representations that allows us to have different particles with different spins. It doesn't force us to have them, but nature tends to take advantage of things that it's allowed to do, and this is one such example. Carroll Cantor says, I understand we cannot exactly describe what happens at the Big Bang because our best theories break down at some point as we approach t equals 0, time equals 0. What exactly breaks down? How and when? That's a very good question, because I've certainly many times myself said our best theories break down near a singularity. You're absolutely welcome to ask what exactly breaks down. Well, and I think that the simple answer is going to kind of sound maybe too simple, but I think it's actually also correct, is that our equations for the theories, right, whether it's general relativity or quantum mechanics or whatever, these are theories that run under differential equations that tell us how things change from one point to point in space, one moment to moment in time, or whatever. Differential equations work with functions, and to be well defined, in other words, to not blow up, functions are maps from space-time or whatever underlying domain you have to numbers, to real numbers, to complex numbers, or what have you. Those numbers have to be finite, right? The actual real numbers don't include infinity. You can add infinity and talk about arithmetic that way, but real sensible fields and things like that have to have finite values at every point. If they have infinite values, especially for something that's supposed to be physically relevant, I mean, a sort of coordinate value can be infinite. That's fine because that's something a human being makes up. But something that's supposed to be physical and tangible, like an energy density, the amount of energy per cubic centimeter, that had better not be infinite or you're in trouble because you can't take a derivative of infinity and therefore you can't plug it into a differential equation. That's exactly what happens, according to general relativity, at a singularity, in a black hole or the Big Bang or whatever. Physical quantities like the curvature of space-time, the energy density, and so forth blow up. They become infinite. That's what blows up, and therefore the handle we have on how things behave in the world, which are these differential equations, break down. They no longer tell you what happens next. If you hit a singularity in your differential equations, you can't continue beyond it. You don't have any prediction for what is supposed to be beyond that point. So that's the sense in which general relativity breaks down at a singularity. General relativity is not true, right? It doesn't include quantum mechanics, and therefore physics is not bothered by that. Our best theories right now are bothered by it. Anonymous asks, suppose a thought experiment of a modern-day extopia, where the operational U.S. voting system is replaced by a perfectly calibrated, mandatory AI voting system that performs ranked choice voting for candidates or even policy decisions using the same approach as recommendation systems. It would vote as you imply based on your behavior and known preferences rather than as you say or hope. What are the moral ramifications of this? Is it a democracy? Is it a humanist society? Is it an invasion of privacy? I don't have deep thoughts on whether it's an invasion of privacy. That would be sort of a technical question. You know, can you have such a system without revealing what individual people's preferences are to others. But I think that it's problematic both in terms of democracy and maybe even in terms of philosophy. The democratic problem is that it's sort of taking the idea of direct democracy and making it much worse. A direct democracy is one where literally every decision by the country or the government or whatever it is made by voting, right? The standard interesting comparison is between they did have direct democracy in various parts of ancient Greece, in ancient Athens, for example, whereas the Romans had a republic, an early idea of the republic. The difference being that, by the way, a republic is not opposed to a democracy. It is a form of democracy. So when people say that we are a republic, not a democracy, you know that they're not actually understanding what is going on. We are both. Being a form of democracy, namely a representative democracy, where rather than directly polling individuals as to what the state should do, we elect representatives, and the representatives have the power. And it's just a much more sensible thing to do because you need some buffer, right? People change their mind too quickly and not always for the right reasons. When we elect representatives, it's not simply trying to elect people who have exactly the same views that we do, okay? That is part of it, but that is absolutely not all of it. Indeed, empirically, people are very bad at voting for people who have close to the same views that they do. There's plenty of other considerations that go into electing representatives. You might want to elect representatives who you think are smarter or wiser or better informed than you are, right? But whether you do that or not, you're giving representatives the responsibility of being the government of the country, which means that they spend their time trying to think about policy issues and trying to become informed and having a staff in the real world that is supposed to be very informed, things that the typical member of the democracy doesn't want to do. I think it's a mistake to think of democracy as primarily a decision-making process. People sometimes do that. They say, like, why do we let dumb people vote or uneducated people vote or whatever? I think that democracy should be thought of as a way of expressing values, of saying that every citizen has an equal right to a voice in what things do. And some citizens might very well say, look, I got things to do other than be super informed about politics and policymaking. Therefore, I'm going to vote for a person who can represent me honorably and wisely, ideally, and then let them make those decisions. And again, empirically, like the Romans did much better than the Greeks at this because the direct democracy doesn't work when you're, fighting battles and the people vote, oh, let's pull back all of our ships now. Nope, let's send them back again. It's just not a very good way to run a country. This AI that can vote as you imply based on your behavior and known preferences seems much worse than that, right? It's like direct from your brain to the decision-making process. It's okay and even good to have some buffer zones in between there. So, I don't think it's a good way of implementing the ideals of democracy. And then the other problem is that philosophically, I worry that it's ill-defined, that there's some purported true value of what your preferences are that this AI is going to be able to perceive. Human beings aren't necessarily that rational, okay? We don't necessarily have a set of true beliefs or preferences that we are simply imperfect at expressing. I think that we are internally a little bit incoherent. And unless you just want to throw away human beings and replace them with something else, that's how it's going to be. And that's how we have to deal with it. So letting people decide who to vote for, I think, is a better system. It might not be the best system, but I think it's a better system than letting AI tell us what we actually are trying to perceive or think or hope for. Stuart Worley says, I think I understand that we get most of the heavy elements from supernova explosions. But when the star explodes, its components in gas form or are some in chunks of solids? Gas form is closer to true here. There's no solids that are being expelled by an exploding supernova or anything like that. The temperatures and the kinetic energies are just far too high. It's not even really gas, strictly speaking, because a gas is supposed to be a collection of atoms or molecules, which means atomic nuclei where the electrons are bound to them. The temperatures and the kinetic energies of the explosion products in a supernova are way too high energy, high temperature for that. You're going to get individual particles. You're going to get nuclei of atoms. You're going to get electrons. You're going to have a plasma at best. But I think that the essence of your question is, are there chunks of stuff being spit out by these supernova stars? No, there are not. Thies Janssen says, I've asked a question twice, and I think it's a good question, but it hasn't been featured on the AMA. How do I know if I should use my priority question? Is this what the priority question is for, or should I draw the conclusion that you won't have a very interesting answer and I shouldn't waste my one priority question on this? I think that's a very good question. That's a very deep question. As I say many times, my basic criterion for picking questions to answer is ones that I think I can say something interesting about. That doesn't mean it's the same questions that people are super interested in getting an answer for, okay? So the priority question idea is supposed to be a compromise between that. Now, given that I haven't chosen a question over and over again, I think you can probably safely assume that I don't think my answer would be interesting for it. Honestly, I think there's a very real argument to be made that no one should ever ask a priority question because I worry that people are sometimes disappointed because they do ask their priority question and then my answer isn't interesting. Well, I told you that. I told you that I didn't think my answer was going to be interesting if you kept asking it as a non-priority question and I didn't choose to answer it. That is the most likely outcome. Yes, absolutely. So the priority question mechanism is supposed to be when you and I disagree about whether or not my answer to your question would be interesting. That's what you have to ask yourself. What can I tell you? You rolls your dice and you takes your chances. Philip Rothland says, in your reflection on the Christoph Koch episode, you mentioned choosing to stay on your prepared path rather than diving into a debate on physicalism versus idealism. As a psychological consultant, I'm aware of how the discussions we make during a conversation shape its outcome. Beyond sticking to structure, do you have other guiding principles for how you navigate conversations, and how have these evolved since you started the podcast? Yeah, another super good question, and I don't know. I have no feeling that I am necessarily super good at this idea of guiding the conversation in real time, given the responses, et cetera, et cetera. There is a specific thing going on with Mindscape in that normally I have people on who have something specific to say, something substantive to say, right? It's not like I have a celebrity on and I want to hear about their upbringing or let them pitch their latest movie or whatever. There's people who I have on the podcast who know something or have some informed opinions about something, and I want to have that be accurately explained, right? So it's a little more purpose-driven in that way than many other more conversational podcasts. On the other hand, well, I guess therefore it makes sense to be, a little bit directed toward making sure that that goal is achieved. On the other hand, it can be fun and illuminating to sort of be surprised by something that comes up, or at least, if not surprised, then at least something comes up that wasn't completely anticipated, and to roll with that for a while and to see where you go. The only thing is, are you going in a productive direction or not? I know that people love debates. I get it. They want to hear, X versus Y. It's just not my style that much. I participated in debates and there's a place for them, but it's not what I love. I would like you to think. I don't want you to be told how to think by me or somebody else. I want you to hear the best possible presentation of a view, and I want you to think for yourself about what it is that you think is true. So I will very happily register that I don't agree, and I will try to briefly state why I don't agree, and then I will move on, okay? Physicalism versus idealism in particular is something that I'm not sure a debate about that would be enlightening at all, right? It might be slightly diverting for a moment, but with Christoph, we had real stuff to talk about consciousness and things like that, and I wanted to get to that. So when you ask, do I have other guiding principles for how you navigate conversations and have these evolved? I do think that I'm more open to diversions now than I was at the beginning. I'm more sort of comfortable with that. I'm less like, no, got to stop that, got to cut that off, got to get to my next talking point. The number of talking points I have in mind has shrunk over time as I'm more comfortable with just talking around a few basic points. But a lot of these people have written books, and somewhere in chapter 8 of their book is some really interesting thing. I live in fear that because of the direction that I choose for a conversation, the guest is left not having an opportunity to say something really interesting that they have to say, right? So my job is to provide the conversational landscape in which they have the opportunities to say all these interesting things. My secondary job is to make sure that them saying it is done at a level where people can follow along and things like that. But I think that's my primary job. And again, that's a feature of my particular podcast. It might not be a feature of someone else's. Speaking of which, Sam Wagner says, would you consider going on Lex Fridman or Joe Rogan again and talk about what Trump, Elon are doing to science in the United States? I'm not a fan of either, especially Rogan, but I just heard Lex interview Ezra Klein and his co-author, and it honestly gave me some optimism for the future of the country. They were compelling. They were heavily critical of Trump and Musk, yet the comments on the YouTube videos were overwhelmingly positive. I would love to see you get in front of a broad audience and potentially change minds. Again, we have just a roll of really good questions here that I've chosen myself for the AMA out of the wonderful questions that our Patreon supporters have supplied, because it's tricky. I do think that Lex and Joe are two different people, two different podcasts. Lex Fridman in particular is a big supporter of Elon Musk, and I am absolutely not a supporter of Elon Musk. I think that Lex is just wrong. But I would have zero trouble going on Lex Fridman's podcast. I think that he's a good faith interlocutor. I'm happy to talk to people I disagree with. He has a big audience. I'm happy to try to reach it. Joe Rogan is a more complicated case. I do think, again, people have said this, and I'll say it, like, as a person, I don't have any problems with Joe Rogan. I do think that the pandemic kind of broke his brain a little bit, and he was always happy to be a conspiracy theorist, but the kinds of conspiracy theorizing that he got into became uglier after the pandemic, and the fact that he supported Trump is just sort of unconscionable. But he does have a big audience. And one of the things about Joe is that he will, for better or for worse, he will have all sorts of people on and he'll listen to them. And for the moment that he's talking to them, he will agree with them, even if they completely contradict what the person he talked to yesterday said. Okay. And again, that's for better or for worse. But I think it's super duper important that people who have good views try to reach out and talk to people who have bad views. Joe Rogan has in many ways become very anti-science in ways that I'd find very difficult to get along with. And so I've not been invited on, and I've not tried to invite myself, and I have no plans to do that. So probably I'll never appear on that podcast again. If I were invited, I would have to think about it. I think that if I were invited, the only way that I would ever go on is if I said, I'm not happy to go on, but I'm willing to go on, but only if we can talk about Donald Trump and politics and all these things that I'd rather not talk about, but I do feel a responsibility to correct a lot of the bullshit and nonsense that has been spewed on this podcast, okay? Is that worth doing? Maybe. Maybe there's probably better people than I to actually be the person doing that. But in any case, I haven't been invited, so I don't think it's a very relevant question. Eli Reams said, when you tune a guitar and increase the tension of the strings, would this energy from the tightening of the string add a small amount of mass to the guitar, causing it to weigh a minuscule amount more than before until the tension is transferred away? Yes, absolutely. I mean, you're definitely adding energy to it. The simple rule of thumb, if you want to know, am I adding energy to a system or taking energy away? It's a very simple rule of thumb. It doesn't always work. But the thing is, do you have to do work to make this transformation happen? If it is effort for you to tune the tuning knobs and increase the tension of the strings, then you are increasing the energy of the system. You are putting energy in, and that energy is being captured by the increased tension of the strings. And then the guitar is an object that you can analyze at rest, and at rest, the rest energy of the guitar is equal to its mass times the speed of light squared. And the nice thing about an equation like E equals mc squared is it works both ways. If you know the mass, you can figure out the rest energy. But also, if you know that you've increased the energy, then you've increased the mass. There you go. Yeah. Same thing would be true if I had a box of gas and I heated it up. So it's at a higher temperature. Now the mass is higher, even though the individual atoms inside are exactly the same atoms you had before. Polina Vino says, what do you think about the dome paradox? Norton's dome is a thought experiment that exhibits non-deterministic system within the bounds of Newtonian mechanics. Suppose there is a ball, and now Polina Vino is describing Norton's dome. Suppose there is a ball sitting perfectly balanced on top of a dome of a particular shape. Roughly speaking, the paradox states that there are solutions to the differential equations of motion that correspond to the ball starting to roll down at any point in time. In other words, the ball can just sit right exactly on the top of the dome, and at whatever moment you want, it can start rolling. And that is 100% compatible with the Newtonian equations of motion. That's an indeterministic example. This somehow does, I'm back to the question again. This somehow does not seem counterintuitive to me, perhaps because if that ball were interacting with any clocks in its vicinity, the Newtonian equations would look very different than in the example system. So this type of non-determinism would never happen whenever timekeeping is being done. So you lost me at the end there. I have no idea what the clocks have to do with it. Unless the clocks are literally bumping into the dome, I really don't think that the clocks matter. But I think it's a cute example with almost no practical consequences for a couple of reasons. Number one, most obviously, mathematically speaking, the conditions that are actually giving rise to non-deterministic behavior are a set of measure zero, which is a way of saying you need an infinite amount of precise fine-tuning to make it work. If you put that ball on top of the dome anywhere but precisely at the top, then it's perfectly deterministic behavior. And if the shape of the dome is anything but exactly what it needs to be, then you will get perfectly deterministic behavior. So basically, this is just a kind of a loophole that John Norton found, again, very cleverly, in Isaac Newton's equations of motion. But the other reason why it's not that important to me is because it's classical. All right, the world is not classical, the world is quantum mechanical. The possibility of finding such a loophole in Newton's laws, in the deterministic nature of Newton's laws, is because the Newtonian equations are nonlinear. They're sort of complicated in a particular way. The Schrodinger equation has no such loopholes. It is a linear equation. It is 100% deterministic. So this is basically finding a measure zero loophole in the deterministic nature of the classical limit of quantum mechanics, something that I think is cute and amusing, but not deep or profound or worrying me about the nature of reality. Mark Robinson says, given the accelerating complexity of information processing and technological development, do you think a future technological singularity or two could lead over 1 billion years or so to entities capable of manipulating matter and energy on cosmic scales? Could that offer an alternative explanation for dark matter since 8 billion years ago and dark energy? So let me skip ahead and say no, it could not offer an explanation for dark matter and dark energy because we have excellent reason to believe on the basis of data that those things have existed a lot longer than that. In dark matter's case in particular, dark energy is harder because it only started dominating relatively recently. But for the case of dark energy, even though it dominated only relatively recently, it's spread out equally throughout the universe. So it's not localized to where stuff is, much less conscious creatures. For dark matter, it was there before the cosmic microwave background was formed, 380,000 years after the Big Bang, where there's really no possibility of technological civilizations doing anything. So it doesn't help with dark matter or dark energy. Let's just say that. The bigger question of whether or not it's even possible to manipulate matter and energy over cosmic scales is a trickier one. You know, the laws of physics don't in principle get in the way of that, but what gets in the way of it in some sense is time, okay? Cosmic scales are pretty big. I don't know what you mean by cosmic scales. The galaxy is some tens of thousands of light years across. but distances between galaxies are millions or more of light years, okay? So to send a single signal, 1 million light years, and have it come back takes 2 million light years, right? That's 2 million years, sorry, at best. So an ordinary sort of technological system has signals bouncing back and forth a lot, very, very, very frequently. The computer in front of you or the brain inside your head have a whole bunch of signals being passed back and forth throughout the whole system very, very rapidly. When you think about cosmic scales, that is simply unfeasible. It would take more than billions of years to send 1 million signals back and forth, and you don't have that many billions of years in the lifetime of the universe. And in some sense, you never will. The universe is accelerating, and maybe it lasts forever, but that means that other galaxies are disappearing from our view. There's a certain set of galaxies, the local group of galaxies, that will still stick around. And basically, that gives you an upper limit for how large any kind of coherent structure caused by technologically advanced civilizations could possibly be, right? Given that, it'll take a certain amount of time for that to happen. By the time that happens, all the other galaxies will be inaccessible to us. So we have the local group available to us. It'll be far in the future at best, but that I'm trying to talk about limits of principle, not limits of practice. So it's funny to think that the first question we had in the AMA is about we'll never get to Alpha Centauri, and this question is about we're going to harness a galaxy or a cluster of galaxies worth of energy to do something. I think it is important to distinguish between what is allowed by the laws of physics, what is allowed by the realities of our cosmic situation, and what is actually technologically feasible in some plausible future history. I would say that manipulating matter on scales as big as a galaxy or a cluster of galaxies is allowed by the laws of physics, right on the boundary of being allowed by cosmological configurations, not really anywhere close to being allowed by plausible technological progress. Anonymous says, I've heard it suggested that our president could be a Russian operative or otherwise working to fulfill Russian aims. I have to admit that the Russian agent theory holds a good bit of explanatory power across multiple fronts of the administration's actions, not just foreign policy. What level of credence would you give the Russian agent theory? Very low credence. I don't think that that's a very plausible way of accounting for Donald Trump's various actions for a number of reasons. Primarily because, it's kind of a conspiracy theory, or at least conspiratorial. Usually conspiracy theories are implausible just because they require many, many moving parts. This one requires fewer. I get that. And for those of you who don't know, there have been multiple KGB agents, ex-KGB agents, because the KGB doesn't exist anymore, who have claimed that they did try to recruit Donald Trump as a Russian asset. But the other reason is I just don't think that he would go for that. I don't think that's the kind of person he is. It's possible that the Russians have some either compromising information or some financial entanglements that cause him to be sympathetic to their aims. I think that's completely plausible, very, very consistent with the data that we have. But that's a level different than being an agent, which I think is not needed to explain any of what we've seen. I mean, here's one story. Columbia University has been one of the universities that have been targeted by the Trump administration by removal of funds. They lost $400 million. Columbia University was taken away by the Trump administration. Remember that number, $400 million. It turns out that Donald Trump has a long-running feud with Columbia University dating back more than 2 decades when Columbia was looking to expand. And Donald Trump had a plot of land in New York that he was trying to offload. It was near Lincoln Center, and he was trying to sell it, and he offered it to Columbia as sort of a satellite campus. And Columbia said no. After some negotiations, they were originally interested, but they went for land that was much closer to the existing campus, which makes perfect sense. One thing about university is it's useful if different people can walk to each other and actually communicate and talk and so forth. So that makes perfect sense. Donald Trump didn't see it that way. He thought that it was a betrayal, blah, 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 blah. The amount of money that Donald Trump wanted for his plot of land to sell to Colombia was $400 million. It is not a coincidence that that is precisely the amount that Colombia was docked in recent days, because at heart, he's kind of a petty gangster. He's a greedy guy who holds grudges and thinks of the world in sort of gangster, mafioso kind of terms, right? That's why he thinks that these tariffs are going to bring people to their knees, because it's a power play. It's a demonstration of influence, like a mob gang boss, right? But there's no Russian involvement with any of that. I think you do yourself a disservice by trying to interpret his various actions through that particular lens. Casey Mahone says, when setting up my iPhone, it said that I said I was interested in articles about science. Therefore, I regularly get shown articles from Popular Mechanics, which usually makes me laugh. Today's article was A Scientist Thinks We Live in a Simulation. Are these kinds of articles a net positive or negative for science communication? On the one hand, they may get people interested. On the other hand, they're mostly complete clickbait garbage. I think, it's a complicated question. I have no problem with an article at the popular level saying we might live in a simulation. I would vastly prefer a robust, healthy, scientific communication ecosystem that included skeptical articles as well. I think that the problem is not so much clickbait. The problem is that we have, and this is someone who is both a science communicator and married to a professional journalist, it's becoming easier and easier to churn out bad science articles. Nothing special about science here, right? You could say the same about sports or business or politics or whatever. It's easy either through AI or just through cheap, bad writing and ripping off other people's writing to churn out large amounts of content that people will click on, even though the quality is very, very low. And I think that's a problem. And when you look at, what are the warning signs? If you're, as a reader, how do you know that you're clicking on some garbage article rather than a good one? Look to see if there are quotes from people who are not the scientists that are the primary subject of the article, right? Like a real journalist will try to triangulate whether or not what they're talking about makes sense by talking to other experts. And what you see in the literature, in the media these days, is fewer and fewer articles that do that. Many of them are just warmed over press releases or whatever. I think it's a huge problem overall, but I think the locus of the problem is just the low effort being given to good journalistic practices rather than a particular topic area or the desire to get clicks or anything like that. Greg Wilson says, I appreciated your solo episode on the nature of time. Although that episode didn't touch much on the arrow of time, I was wondering, do you think it's truly possible to experimentally verify that any law of physics is truly time reversible? My intuition is that even the most carefully constructed experiment would always be contaminated by the second law in some way. Are there any examples of exact time reversible physics that can be demonstrated experimentally? Well, it depends on what you mean by exact. Science doesn't work in exactness, ever. That's not how science goes. You collect a bunch of data, you propose hypotheses to purportedly account for the data, and you think about the hypotheses that fit the data the best. The best hypotheses we have right now is that time reversal invariance, or some souped up version of time reversal invariance that also involves charge and parity, is an exact symmetry of the microscopic laws of nature. We've done experiments looking for violations and haven't seen any. Just like with the measurement question earlier, you can't ever get to exactness in time reversibility, but you can get as close as you want. In particular, it's very often not that you do an experiment and then reverse the dynamics of the same experiment, but you do two different experiments. You let system A evolve into system B, and then you let system B evolve into system A, and you ask, is it equally likely or does it happen equally with an equal quantum amplitude or something like that? So it's not that there is ever exact time reversal physics, it's that time reversible physics. It's that that's the best explanation for what we see right now, but of course we always keep an open mind. Paul Cousin says, in episode 298, Jeff Lichtman argued that we might never be able to really understand the brain, as it would imply that we come up with some compressed version of its complexity. And there might not be such a thing. There is no simplification. If there were, the brains would be much simpler. You seemed rather convinced. Given that brains have been optimized with a constraint that their structure must go through the bottleneck of the reproductive process, which seems to me like a rather drastic form of compression, I fail to get the argument. What am I missing? Well, I mean, it's trivially true that we can understand things about the brain in a very compressed way. That's not any problem whatsoever. But I think that Jeff's point is that there will always be a level of exact reproduction that is essentially impossible. Not super duper physically impossible, but way, way, way beyond what we can imagine right now because the brain is just so complicated. It's very much like saying, if you have a painting, the Mona Lisa, can you describe the Mona Lisa to someone who's never seen it? Sure, you can, but it's not exactly the same as showing them the painting, right? Or showing them an exact reproduction of the painting. You're passing through some filter that loses information when you try to capture aspects of the system in a compressed form. There's a substantive question here, which is maybe what you're getting at, which is given that the brain was not intelligently designed, right? Given that it did evolve through evolution and so forth, shouldn't we expect that there are some aspects of it that are highly compressible? Maybe. I think that's an empirical question. I think that's, Lichtman is saying no, actually. The brain, given what it's trying to do, is close to as compressible as it can be. That is his point of view. Is that point of view correct or not? I truly don't know. I think that's a science question that I'm not an expert in. Joan Beluda says, as a parent, I faced one of those universal and deeply human moments when one of my kids first realized what death is and that it will eventually happen to them too. It's a powerful and emotional turning point for any child. If you were in that situation, how would you approach the answer? What's the best way in your view to talk about death with children, honestly, without sugarcoating it, but also in a way that doesn't traumatize them or create fear? How can we explain something so final through a scientific lens yet still offer comfort? Well, I don't think that I'm the person to offer child rearing advice, to be very honest. So I can offer some offhand philosophical thoughts on the matter, and you can deal with them better than I can in terms of actually talking to your child. I went through that moment when I was a kid. At some point, I literally woke up crying in bed one night thinking, oh my God, one day, I'm going to be dead, and my grandparents are going to be dead, and my parents are going to be dead, and my brother's going to be dead. That we'll all be dead. Oh my God, this is terrible. But I got over it pretty quickly, actually. I remembered it, but you learn to deal with it. I don't think there's a secret to learning to deal with it. I think that my personal feeling is that it would be a mistake to sugarcoat it, it would be a mistake to try to hide the reality of it. I think that personally, what I would try to do is to give some credit to the kids that they can learn to deal with it. Some will learn to deal with it better than others, but I don't think that by offering any particular not exactly true statement that you're making it easier on them. Human beings live for a finite period. That's always been what's happening. That's always going to be what happens. The period is still very long, compared to our moment-to-moment lives. And so you have a lot to look forward to, and it's in the natural progression of things that new people come into existence, old people go away, and that's okay. It might not be what you immediately want in the moment. It is always tragic when someone who you care about dies, but the larger picture is a perfectly sensible one. And I think that you have to let the children come to terms with that in whatever way they can best do. Frank Leon Rose says, in the cocktail episode, there was a discussion of how some drinks, or curries for that matter, with more parts are more resilient to change and modification. They keep working within a wide range. It occurred to me that in contrast, there are some systems with many parts where every part has to fit perfectly in the whole, like a pocket watch or a laptop. These systems are not resilient to changes in constituents. Is this a well-explored characteristic by which complex systems can be classified? Is there discussion in complex system research of scales of resilience, for example? For example, a biological system may tolerate the loss of cells, but not the loss of organs. I think that there's been some research. In fact, Chris Kempis, recent Mindscape guest, he and I were talking when I was at SFI recently about robustness and resilience and the ability of systems to repair themselves. But I don't know. I don't know if there's a conventional wisdom or sort of a set of settled results that point to one thing versus another. I mean, one obvious, very crucial difference is between evolved systems and designed systems. Usually, evolved systems, I shouldn't say usually, but as a rough first pass, evolution is not teleological, right? It doesn't look to the future, but what it does is remember, in some sense, the past, in the sense that it has a record of having failed. In certain systems didn't pass on their genes, so that counts as failures. Other systems did pass on their genes, that counts as success. And so what are the systems that are going to succeed? Rather than trying to anticipate the future challenges, they're ones that are pretty general purpose and resilient, right? Because the next generation of challenges might be different than the last one. So biological systems tend to be self-repairing, general purpose, robust in that way. Sure, you cannot lose an organ, but no system can lose, some large percentage of itself and keep going. There's always going to be some ability to kill a complex system to stop it from doing its job. But you can break a bone and it will repair, right? Whereas if you get a flat tire, most cars do not have self-repairing flat tires. Or, even if more dramatically, if I don't know what is the correct failure mode of the modern car. If a piston cracks, there's no self-repair mechanism in there. Trying to get an analogy for the broken leg. And I think the laptop is the same way, and I think that that's because these are designed by people with some, fail-safe mechanisms in there, et cetera, but mostly they're designed with the idea that you are going to anticipate ahead of time what the challenges are, and you're going to build them, and you're trying to optimize for cost and space and volume of creating them and speed with which you can make new models and things like that. A whole bunch of things other than simple survival, which is why I think that, the future generation of robots will, the real robots that become comparable to biological systems will actually end up resembling biological systems. Biology has solved a lot of these problems ahead of time. We always in our brains or in our science fiction shows imagine these robots that are made of metal, which is just a terrible way to make robots. Metal is, something that bends and breaks. You got to make robots out of little microscopic things that group together to make a collective. That's what biology does, because that makes self-repair much, much easier. And I think that's going to be the future of humanoid kind of robots. Yazan al-Hajari says, I'm originally from Syria, living in the U.S., and I've been struggling with how to express my artistic voice in a way that promotes science, truth, and liberation, especially in a region like the Arab world, where religious fundamentalism and traditional thinking often block progress. I try to use storytelling, music, and film to inspire curiosity, but I've come to feel that without sharp criticism of religion and outdated ideas, true change is almost impossible. At the same time, that kind of criticism can be dangerous or shut people down completely. I'd love to know, how would you approach this tension? What is your advice for someone like me who wants to push people toward new perspectives, but is caught between the need for honest critique and the risk of alienation or worse? I think that this kind of situation requires many, many different strategies. It's not a one-size-fits-all thing. There's absolutely a place for straightforward critique to say fundamentalism is bad, God doesn't exist, totalitarianism is bad, human rights are important, whatever that is. There's some value in being straightforward and being impossible to misinterpret. There's also absolutely value in being more subtle, right? Oftentimes, when it comes to just in the more specific, much lower stakes world of debates about the existence of God within Western cultures, where you are allowed to say on either side without going to jail, it's more important to be, to present a compelling role model, an example of a life well lived as whatever it is you're trying to advocate for, rather than to try to, beat your opponent in a debate or something like that, right? So I think that there's absolutely a huge role for subtle satire in the form of art or music or literature or whatever, or even just celebration of whatever it is you're trying to celebrate. And you have to be a little careful when you're thinking about, is it working or not? Because it might very well be working, but working on a time scale where you don't see it, right? It is not true that people instantly change their minds when they are faced with a good argument, nor is it even true that they let you know when they have changed their minds, certainly not when they're close to changing their minds. So I know it can be frustrating, to do art like that or even to say things directly in some polemical fashion and not see instantaneous change come about because of that, but all of it plays a role. Every little bit contributes to the bigger thing. We live in a world where, among other things, there's a lot of people living in the world. There's a lot of effect you need to have to change the world in any noticeable way. You can't be frustrated because those effects take a lot of time or don't show immediate payoffs. It's a marathon, not a sprint. Henry Jacobs says, I read The Big Picture a few years ago. I vaguely remember an idea along the lines of the meaningfulness of your life can be partially measured by how much information you reveal to the world. Sorry if I'm butchering it. It was an awesome read, and I just want to verify I didn't hallucinate this notion. How much am I butchering this? That doesn't sound familiar to me, honestly. I don't think I said something like that. I have said things adjacent to that in the past. I didn't honestly take the time to look at what exactly I said in The Big Picture. Sorry about that. But certainly I said, when it comes to the meaningfulness of life, that there is no one such thing as the meaningfulness of life, that different people will get meaningfulness in their lives from different sources. So there can be many different ways of finding meaningfulness. One of them might be the information you reveal to the world. I've talked about another way is, to think about the path of least resistance that people can take through the world. And if you find that the path of least resistance is not the perfect path, meaningfulness can come from resisting that path, from taking a more difficult path in the purpose of making the world a better place, and by whatever standards you think would be a better place. But I also absolutely 100% believe that you can have a meaningful life without revealing any information to the world, without doing any struggle whatsoever. Because I really truly believe what I say when I say that meaningfulness in life is individual. To some people, meaningfulness in life is just having a family and living with them in relative comfort and stability, right? And keeping the children happy. To some other people in life, it might just be, playing video games all the time, going to work, getting enough money to afford good video games and playing them. That's okay. I am not going to criticize those people if they are indeed fulfilled by doing that. I'm not saying you should be fulfilled by doing that. I'm not saying there is anything either right or wrong about that. But I do think that it's good that different people have different versions of getting meaningfulness into their lives. And that's a hard lesson for people to really take to heart, but I actually do believe it. Evan Dorn says, I'm fascinated by the idea of the core theory as presented in The Biggest Ideas, Volume 2. If I understood correctly, you said that general relativity can indeed be reconciled with quantum field theory and the Standard Model, at least in the low-energy, low-curvature regime. But I've heard other physicists explain that QM and GR are deeply incompatible, in part because masses in quantum mechanics can have uncertain position or be in a superposition of different positions, while GR associates masses with definite positions. That objection, if true, would seem to apply at all energy and curvature scales. Can you help bridge this gap in understanding for me? Yes, I can. This is the kind of question I like because I can answer it. You have to distinguish between general relativity and gravity. You are completely correct that general relativity is a classical theory. It associates masses and, more generally, energy and momentum with definite positions, okay? Because it's a classical theory. In classical physics, that's what masses and energy have. They have definite positions. Quantum mechanics doesn't do that. Quantum mechanics has wave functions and things like that. So I know that some people like Jonathan Oppenheim have tried to really push the idea that maybe matter is quantum mechanical and gravity is actually classical. I don't think that there's any chance that that's true, any realistic chance that that's true, but good for him for trying. What I'm talking about is gravity, but quantum gravity, not classical general relativity. I'm saying that we do have perfectly acceptable quantum understanding of gravity in the weak field, low energy, low curvature regime. It's not general relativity. It's truly quantum gravity. It's the metric has a wave function, just like the electron field or the electromagnetic field or the gluon fields all have wave functions, okay? We can do that. It is not general relativity. It has a classical limit of being general relativity in the weak field regime, but it is truly a quantum theory. So masses do not have definite positions and so on, and the metric doesn't have a definite value. That's how it's supposed to work. Carl Einerson says, can you please help me get to grasp with the fact that anything falling into a black hole will never reach the event horizon in this universe's lifespan, or am I getting this whole thing wrong? Yes, I think that in some sense you're getting this whole thing wrong. This is a classic issue about black holes. It depends on whose point of view you are following. In general relativity, there's no one unique way to think about the passage of time. Different people are going to measure time along their individual clocks, and then there's different choices you could make about how to knit those different viewpoints into a universal clock. But there's no right or wrong way to do it. I guess there's wrong ways to do it, but there's no right way to do it. There's many, many different possibilities. So the thing to say about the black hole is if a person falls into the black hole carrying a clock with them, they will reach the event horizon and continue right on past the event horizon in a very finite period of time, a very calculable period of time. If you take a general relativity course, you will probably calculate what your clock will read when you fall into the event horizon given some appropriate initial conditions. But from the point of view of someone who stays outside the black hole, as their time goes on, they don't see the person past the event horizon. They just see the person get closer and closer to the event horizon. Technically speaking, they eventually stop seeing that person because it takes longer and longer for photons to be emitted by that person falling in, and the photons that are emitted are increasingly redshifted, so they're harder to detect. So for practical purposes, they stop seeing the person who falls into the event horizon. But in principle, in the world of like test particles and perfect idealizations, an infinitely tiny particle would never be seen to cross the event horizon from the point of view of someone outside. That's okay. There's no problem at all. Logically or not. Two different people doing two different things, see two different things, and measure two different things. Jamie says, you sometimes cite the idea of brute facts, but I don't like it. And I think it contradicts your other good ideas, including, and then Jamie lists some ideas that I have. But he continues, usually when you say brute facts, it seems like you're only saying that something is outside the paradigm in question. Maybe we're operating under assumptions or have an effective theory or are participating in a conversation that's part of a tradition. But sometimes it feels like you forgot this modest standpoint and regress to a metaphysical claim about a rock bottom. My question is, am I right? So no, you are not right. When I talk about brute facts, it is almost never saying that something is outside the paradigm in question. That wouldn't be a brute fact. That would just be a relative fact to that paradigm. I really do believe in brute facts. In fact, I think it's perfectly obvious that there are brute facts. I know that not everyone agrees with me, but so be it. For the following reason. There are many different possible worlds, right? In David Lewis's sense, we can imagine all sorts of different worlds that are conceivable but not actual, right? A world where the electron mass was different than what it is right now. That's a different possible world, okay? There's literally an infinite number of possible worlds that are perfectly conceivable, would have perfectly sensible laws of physics, but are different than ours or different initial conditions than ours, etc. Somewhere, you have to make a choice about what the actual world is, right? And given that it could have been some other way, that's a brute fact. Why do we live in this possible world rather than another one? We don't have a very good handle on what the set of possible worlds is because, we can tend to sort of realize, oh, there's a relationship between this fact about the world and that fact about the world that we didn't know about before. So in fact, a world where that relationship didn't exist is not possible, even though we thought it was, that's fine. But it's perfectly obvious to me that there's a lot of possible worlds, and so pinpointing which one we're in is just a brute fact. There's no, even if you could invent a principle that says, oh, the one we're in is the best. It's like, I don't know, the simplest, or the simplest in which life could exist or whatever. The fact that that principle works is a brute fact. You just invented that principle. It could have been otherwise. So I'm not afraid of brute facts. I'm sorry that you don't like them. Alex Dubrow says, I understand your position on mathematical realism. You argue that it's not real in the same way the physical universe is real, and for the most part, I agree. However, when I look at number theory, it often feels like we're exploring an independent landscape rather than constructing arbitrary frameworks. For example, Lagrange's four-square theorem and the intricate unexpected patterns in prime numbers seem to be discoveries rather than inventions. How do you reconcile these seemingly objective structures with your anti-realist stance on mathematics? Well, I want to emphasize my stances on mathematics are not very well defined, okay? I've never claimed to have very good understandings of the stances I have, but I have the stances I have until someone convinces me otherwise. I have only recently, due to a student who I've been talking to, Tariq Lacour, been introduced to a new way of thinking about the philosophy of mathematics, which maybe I like. I don't know. I need to think about it. The traditional stances towards realism are either Platonic realism, that is to say you think of mathematical objects and structures as really truly existing in some sense, or nominalism. So if you remember, Jody Azuni appeared on the podcast. He's a famous nominalist. He thinks that things like numbers are just names. That's where the word nominalist comes from. Names that we give to classes of things that can actually appear. When you say the number 4, you're thinking of sort of the prospective possible set of all possible sets of objects that have 4 objects in them. And we call that the number 4. The problem for nominalism is something like what you say, which is that there is all of this structure in mathematics that seems highly non-arbitrary, whereas handing out names to things kind of seems arbitrary. So what I would have said, and I still will say it tentatively, is that there is a distinction that I learned from Justin Clark-Doan, another previous Mindscape guest, between realism and objectivity. Those are two different things. You can believe that mathematical structures are objective, that is to say, not subjective. In other words, everyone would agree on what they are without thinking they exist in the same way the physical world does. I'm not sure how good that distinction is, but at least it's plausible at that level. But the new perspective I just learned of is called Aristotelian realism about mathematics. It tries to think of mathematical objects more like we think about physical concepts. The number 2 or the number 4, rather, to stick with our same example, literally is just the theoretical construct we use to discuss collections of 4 objects. I think James Franklin is the guy who's been a champion of Aristotelian realism. So it's a more grounded kind of realism than Platonic realism, which makes perfect sense if you remember Plato and Aristotle as they actually were. The Aristotelian realists literally quote, some passages from Aristotle in thinking about the philosophy of mathematics. So it purports to be a middle ground between Platonic realism and nominalism about mathematical objects. I don't know anything about it that much. You can Google. There's an article that Franklin wrote that I looked at very briefly. Maybe it's a good idea. Maybe it's not. I really don't know. But the dramatic change to my belief system that I could imagine happening, I'm not sure that it's going to happen or not, probably not, but I can imagine happening, is if the distinction between math and science just dissolves in my mind. In my mind, there's a super strong distinction between math and science. Math is about the set of all possible logical structures, and science is about the actual structure in which we live. So the idea would be that actually math is about that too, but just like physics can imagine theories that aren't right, and therefore don't apply to the physical world, math can imagine axiomatic systems that don't apply to the physical world either, to really sort of put those two kinds of operations more on a single footing. That would certainly that would be in conflict with things I've been saying for decades now about the difference between math and science. So we'll have to see if I go into that, if I eventually buy that or not after thinking about it more. But meanwhile, I know perfectly well that the challenge to anti-realists in mathematics is that math is so objectively reliable, right? Once you have the axioms, we all prove the same theorems. That's a fact about math. How does the anti-realist deal with that? That's a very good question. Leo Behe says, do you think it's important to find some external justification for why you're right about some topic, beyond just saying I got it right and other people didn't? I found that it's far too easy for me personally to attribute other people's views to ignorance or bad intent, and I've become more interested in challenging myself to find some reasonable explanation for why my opinion is the more likely to be correct. A hypothetical example would be that even if I believe that vaccines don't work, I should also consider why I would be more likely to get it right than the people who study the topic for their whole lives. Do you ever apply this type of thinking to yourself? So it's possible I'm not completely understanding your question, but if I am, then yes, I absolutely apply this thinking to myself all the time. You have a lot of beliefs. We all have a lot of beliefs. Our set of beliefs have varying degrees of support from other beliefs and information that we have. Some things we believe just because we were told once, or we have a vague recollection, or we don't even remember why. Others, we have elaborate, very believable justifications for them. The more important and controversial the belief is, the more important it is to have good justifications for why you believe them, good reasons why. I will mention in passing that you can go back to the podcast we did with Hugo Mercier about why the idea of a reason why you believe something ever came to exist in human discourse. And he makes the point that, or at least he argues, that it's a social thing, not an intrinsically rational thing. We didn't invent reasons because of our desire to justify to ourselves, but because of our desire to justify to other human beings why we held one belief rather than another. That's perfectly legit. That's perfectly good reason to have invented reasons. Roland says, is the Higgs field uniform throughout the universe? Could it be greater in one area than another? If so, would a given amount of matter have more mass in that area, and could this cause matter or mass inconsistencies that dark matter is being attributed? So the Higgs field is more or less uniform throughout the universe, yes. And the reason why is because it takes an enormous amount of energy to change the value of the Higgs field throughout the universe. This is reflected in the fact that if you do change the Higgs field, if you poke it to change its value at any one point, just a little tiny bit, what you do is you make a Higgs boson, right? And Higgs bosons are heavy. They're 125 billion electron volts or whatever it is, over 100 times the mass of a proton. So that's, number one, a lot of energy to put into a tiny region of space. And then number two, it instantly dissipates because fields are coupled to each other. So that Higgs field decays, that Higgs boson, the excitation, the vibration in the Higgs field, decays into other things right away. The lifetime of the Higgs boson is about 1 zeptosecond, 10 to the minus 21 seconds. So the Higgs field very, very rapidly settles down to a uniform value everywhere. Nothing to do with dark matter, etc. Scientists would have thought of that if that was a plausible way of thinking. Jim Murphy says, as I get older, I start to realize that some of my more lofty goals are no longer practical. Things like becoming a chess grandmaster just aren't in the cards anymore. Have you had any similar realizations, and how do you come to peace with the fact that you can't do everything you wanted to do in life? Yeah, I mean, that's going to be very, very true. Like at some point, I hate to say this, but at some point, any one of us will have less than a week to live. We don't know when exactly that point will be. But if you haven't learned how to play chess yet and you have less than a week to live, you're not going to reach grandmaster status. As we get older, the space of possibilities in our future lives decreases over time. On the other hand, we get better at making choices, I hope. At least let's imagine. Let's be optimistic for the moment. Let's imagine that our wisdom that we accrue through the years makes us better at making choices about our life. So even though we have less time to do things, we're better at allocating the time that we have, okay? So yeah, I've come to peace with the fact that you can't do everything you want to do in life. There's a lot of things I want to do. Like I am constantly inventing, new papers I want to write, new questions I want to answer scientifically, new books I want to write, whatever. Not to mention, going traveling and experiencing things and things like that. There's no possible way that I have enough time in my life to do all of these things. So intellectually, I'm completely at ease with that fact. Personally, it makes me sad, but that's the way it is. As we said, if we're asking 10-year-old children to deal with this, then I think the professors who have been around for many more decades than that should be able to accept it. Kyle Cabasares says, given the political climate in America and the defunding of key institutions that help finance university research, do you have practical recommendations for high school students and undergraduates who wish to pursue scientific careers? I'm of two minds about this. On the one hand, I think that it's perfectly prudent and sensible to be realistic about the prospects for scientific careers right now. It's easier for me to think about this in the context of, an undergraduate going to grad school or graduate students applying for postdocs, because it's easier to predict short-term things than long-term things. If someone's in a high school, things might change over the next 5 or 10 years in ways that I personally can't predict. But certainly we're losing a lot of money. We're losing a lot of infrastructure. We're losing a lot of intellectual resource in terms of knowing how to do things and guidance. We've lost an enormous amount of credibility internationally. So people are going to be much less likely to either come to the United States or send other resources here and so forth. So for all sorts of reasons, it is harder right now to imagine pursuing a scientific career than it was even 6 months ago. Sorry about that. For what it's worth, on the other hand, it might be also more difficult to pursue all sorts of other careers in ways that are hard to predict right now. So I'm not even sure that it is, on a relative scale, harder to do science than anything else. It's just the whole world is feeling very, very uncertain right now. So, I try, even in much better times, to be honest with students who want to do science for a career about, on the one hand, how rewarding it is, on the other hand, how difficult it is just simply get a job at a very down-to-earth practical level. It's always been difficult. If it's more difficult now than it was before, it still has always been difficult. And so, therefore, my own advice is to, of course, you can want to have a career as a scientist, but if you're going to study science at the level of getting a PhD someday, you better do it with the idea that you would consider it to be rewarding even if you didn't end up getting the job, even if you moved your career into something else. And I think that getting a PhD in science is intrinsically rewarding for all sorts of reasons. So I, in good conscience, am happy to recommend that if you're that kind of person, you should pursue science and see where it goes. Matthew Atkins says, your recent conversation with Christoph Koch got me wondering about ontological positions among scientists. After trying on many different metaphysical hats over the years, I've eventually settled on being agnostic about it. Not to imply that I've become a Mysterian, because I'm agnostic about that too. I've come to the conclusion that this is the most scientific mindset to have on the matter, and that it absolutely is consequential, since strongly held metaphysical beliefs are the foundations that dogmas reside upon. As you are a self-proclaimed materialist and one of my favorite intellectual figures, I would love to hear your thoughts or disagreements on this. So I guess I take it that what we're doing here is comparing being a materialist to being an idealist to being, as you say, agnostic about what ontological side to come down on. Of course, yes, you can become dogmatic in whatever beliefs you might have, not just about ontology or metaphysics, but about other things as well. I don't think that's a good argument to not have beliefs. I think that you should do the best you can to believe that what you think are the most plausible things are true. For me, the evidence in favor of materialism is just overwhelmingly strong. It's not even a close call. I see no coherent alternative, idealism-wise or otherwise. So I'm not going to therefore be agnostic just because I'm worried about being dogmatic. I'm pretty dogmatic. I'm dogmatic for good reasons. I have evidence and I have arguments, and those have led me to have one belief. If you're not that, if the evidence that you've been confronted with has left you in a position of honest agnosticism, then that's perfectly okay. Then that's the most intellectually honest thing to do. It would only be dishonest to hold a belief because you were worried about where that belief would take you, rather than having a belief because it's the best fit to the evidence. For me, materialism is far and away the best fit to the evidence. If that makes me dogmatic, then so be it. Jacob Asmuth says, I would love to hear your thoughts about AI trained using reinforcement learning or thinking. These models are trained with a stage where the reward is given based off correct answers, not off of simply predicting the next token. Not only has this shown huge improvements in performance, but also it seems to have a more human-like learning method. In fact, researchers even see spontaneous self-anthropomorphism from models emerge the more you do this, like, oops, I made a mistake in my calculation there. I find these emergent behaviors correlating with intelligence to be really fascinating. Do you think this is AI regurgitation or something more interesting? So I'm not going to actually answer the question because I want to be very clear. I'm not an expert on the technology of AI, okay? So I do not understand the detailed nuances about different methods of training and learning in AI models. But I do want to address the question because I do think that there are a couple of important things that are worth saying. One is, I've tried to portray a nuanced view, which doesn't always come through because people don't like nuanced views. But the nuanced view is, on the one hand, LLMs are super duper useful for many, many purposes. And a lot of people who I follow and read and listen to on the internet are sadly just resistant to understanding how super duper useful LLMs can be. And they are going to change the world in important ways. So I think that's an important thing to note. At the second point, they're not human-like intelligences, nor will they ever be human-like intelligences, for reasons that I've given plenty of times elsewhere. The third point, that's not to say that AI can't be human-like intelligence. It's just not going to be an LLM kind of architecture. It's easy to imagine other kinds of approaches to AI, and I've talked about that with many people here on the podcast. It is still very plausible to imagine human-like intelligences arising by better technologies than that. Better technologies for that purpose. LLMs are perfectly good technologies for the purposes that they're perfectly good at, okay? All right, so all that's stuff I've said before. The one thing extra I want to say here is specifically about this point you raise about how, quote, researchers even see spontaneous self-anthropomorphism from models emerge the more you do this, like, oops, I made a mistake in my calculation here. So again, whether or not this is the result of true a reasoning system that we would recognize as intelligent, the evidence from the existence of statements like that there's anything like intelligence going on, is incredibly weak to the point of practically non-existing. You are literally training the computer program to try to act like an intelligent human being, to try to say things that an intelligent human being would say. You can't be surprised when it ends up saying things like an intelligent human being would say. That's what you told it to do. That's not evidence that it actually has stumbled upon something resembling intelligence. That's just evidence that it's really good in telling you what you want to hear, okay? So that's not to say there couldn't be evidence that there really is some intelligence going on, but those kinds of outputs are not that evidence. You actually need to dig in to what is the reasoning process that is going on, and also you have to think very carefully about what counts as intelligence in human intelligence. It's not a simple problem. You got to really think about it. So is it regurgitation or something more interesting? I have no idea, but the existence of sentences like that did not move my Bayesian needle even a little bit. Peter Newell says, what's the most challenging objection to compatibilism that doesn't just misunderstand the argument? So compatibilism, I presume you mean about free will, in particular the idea that free will is compatible with Determinism at the underlying laws of physics level, or even I think it should be better understood as compatible with mechanism, a mechanical understanding that does not involve thoughts or agency at the microscopic physical level. And the argument for compatibilism is simply that there is a higher level emergent way of thinking about human beings, which seems to necessarily require that we think of those human beings as reasoning agents that make decisions. As I've often said, I've literally never met a human being, no matter what their opinions about free will is, who does not treat other human beings as reasoning agents who make decisions. So even if people claim not to be compatibilist, in fact, they actually are. They're just not admitting it. So what would be the best objection? Easy. Come up with a better theory of human beings. Come up with a better way of getting through life, dealing with other human beings that predicts how they're going to behave more accurately than folk psychology or even sophisticated psychology does, that does not treat them as agents capable of making decisions, right? I'm not quite sure what that theory would look like, but, we have a theory of balls rolling down hills that does not treat them as agents. It just says that they are obeying the following differential equation. So if you have a theory that is not fundamental physics, that gets the same input as the everyday higher level emergent theory that we have of human beings, but does a better job of predicting how they behave and does not refer to agencies or deliberations or choices or anything like that, then you have undermined compatibilism very effectively. Hail Zeus says, in this past February's AMA, you mentioned that you'll be teaching undergrad quantum mechanics at Johns Hopkins next year. What will you be using as your primary text, your own notes or a published textbook? I'm curious about your approach, as some common methods include McIntyre's spin-first approach, Griffiths' Schrodinger first approach, or other common styles like Shankar, Leboeuf, or Zatilli. Yes, I am teaching undergrad quantum mechanics. I've purchased a lot of textbooks on quantum mechanics, let me tell you, and happily tax deductible. But I have a lot of books that I've gone through, and and remember, maybe you don't know, but I do have as a plan, and I've even been making small progress on it, writing a quantum mechanics textbook myself. And the motivation for writing a quantum mechanics textbook is I don't think that the current textbooks are good enough, even though there's many, many of them. And in some ways, they're very good. But in other ways, they're not very good. So I could nitpick and tell you the problems with each different book, but who cares about that? I think that, for those of you who know a little quantum mechanics, there is this bifurcation. There's this split in styles. It used to be that there was only one style, and the style was the following. We know classical mechanics, right? We know, the theory of a ball rolling on a landscape, so it's being pushed around by the slope of the landscape or something like that. So we invent what is called the Hamiltonian, which is a way of having the energy characterized in terms of the momentum and the position. And then we can promote that to an operator on wave functions. So instead of having a particle with a point-like position and momentum, we have a wave function of either position or momentum, and we have a Hamiltonian operator, and that gives us the Schrodinger equation. So we have wave functions replacing particle positions in phase space, and we have the Schrodinger equation telling us how wave functions evolve with time, and then we have a rule that we're going to just slap on there for the outcomes of measurements that is intrinsically random. That's the traditional way of doing it. The good news about that is that the starting point is classical mechanics and particles that have positions and things like that. These are all things the students already know. I'm a huge believer in recognizing that students are not empty vessels into which you pour knowledge. They come with pre-existing beliefs and understandings of some things. So starting with classical mechanics and promoting it to quantum mechanics makes perfect sense. On the other hand, there's a set of problems, because the resulting answer you get for the quantum mechanical theory, even of a single particle moving in a potential, is a vector in an infinite dimensional Hilbert space, as frequent Mindscape listeners will be familiar with. there's a huge number of mathematical issues associated, niceties, not like issues about, we can't deal with this, but dealing with it is subtle and tricky when you have an infinite dimensional Hilbert space. To do it right requires a whole bunch of math that you have to be very, very careful about. That's one problem. And the other problem is that at the end of the day, what you're left with by this reasoning is a differential equation, the Schrodinger equation on a wave function as a function of position. And that is, I don't know how to say this, that is misleadingly normal, conventional looking to a physics student. Physics students have seen differential equations, right? They've seen Newton's laws, they've seen maybe Maxwell's equations or whatever. And from the professor's point of view, it is easy to turn the course on quantum mechanics into a course on solving differential equations, in particular solving the Schrodinger equation. And you can come out of a one-semester course on quantum mechanics thinking that's all quantum mechanics is, just solving the Schrodinger equation over and over again. And words like entanglement and measurement and decoherence and density matrix never appear in your quantum mechanics course. So that's the downside of the traditional approach. In response to this, there is a non-traditional approach that is gaining popularity, which says, look, forget about the classical starting point. Let's think intrinsically quantum mechanically. Let's accept that the world is quantum mechanical, something that I'm very in favor of when it comes to research, thinking intrinsically quantum mechanically. Let's teach students quantum mechanics by thinking about the simplest possible quantum mechanical system, and that is basically a qubit. That can be physically instantiated as a single spin, right? The spin of an electron or something like that. That is a quantum state vector, is described by a quantum state vector that is in a two-dimensional Hilbert space. 2 is much less than infinity, and correspondingly, it's much easier to do the math, to manipulate, to solve all the equations that you want to solve if your physical system is a qubit. You could even add another qubit. Now you have 2 qubits, and it's 2 times 2 equals 4-dimensional Hilbert space, still very easy to deal with. There's a lot going on even in 2-dimensional Hilbert space, but 4 dimensions you can still wrap your brain around. Okay, so in terms of the logical progression of the theory, starting with qubits is much more straightforward. That's a good advantage, and a lot of new textbooks try to do that. The problem is the students are going like, what are we talking about here? Like qubits, spins, block spheres, 2-dimensional Hilbert spaces? Like this is just a complete phase transition, complete change from what they've been learning for 1 or 2 or however many years it's been as physics students. It's a shock to the system that they have trouble dealing with. Therefore, my own approach is to do both. I think it's possible to do both. I think what I will be doing is starting with wave functions, but very quickly saying, in week 2 or 3, look, what do we have here? What have we discovered? We've discovered that quantum states are vectors in Hilbert space. Hilbert space for this particle in a potential is infinite dimensional. Well, could we have a simpler system that we can think about? Oh, yes, let's decrease infinity down to 2 and invent qubits and work from there and just go back and forth from dealing with qubits to dealing with wave functions. For whatever reasons, we all know the reasons, but the traditional textbook approach does one or the other. I'm going to do both. I think the students can handle it. I think it's good for the students. They will both get the grounding in the intuition they have from classical mechanics and a toolbox to use that they can actually see everything explicitly that will let them talk about entanglement, Bell inequalities, decoherence, quantum information, all that stuff. So therefore, I will use textbooks, but I'm going to use a linear combination of textbooks, which I suppose is appropriate in quantum mechanics, a superposition of textbooks, supplemented by my own notes. Brett Slaw says, what are your thoughts on the abundance agenda promoted by Ezra Klein and Derek Thompson's latest book? The basic, I should say, previous Mindscape guest, Ezra Klein. The basic thesis being that progressives should be focusing much more on the supply side of economics, removing constraints that prevent building enough housing, clean energy, and infrastructure. Do you agree with its premises, and do you think it's politically promising as a platform focus for Democrats? Well, look, I know that there's a lot of real-world practical issues here that I am not the expert on, so I can't tell you about details. I am sympathetic to the approach, though, yes. I do think So let's put it this way. I don't know if maybe this is uncharitable. I don't know. Let's be uncharitable. Let's allow ourselves to be a little bit uncharitable. There are some people on the left side of the political spectrum, the liberal side, right, that, well, there's different reasons. I guess what I'm trying to say is there are different reasons to be on the left side of the political spectrum. There's a subset of people who are on the left side of the political spectrum because they are basically scolds. They are moralistic, and they think that they know what it means to be a virtuous person, and they want other people to be their kind of virtue. Jennifer, when we lived in LA, she bought a Prius back in the day when the Prius was the sexy new thing because it was a hybrid and got wonderful gas mileage. And she said she drove it up to a trip to Berkeley, which is the home of some of these leftists. And she said that, when she went to the gas station, because you still need some gas in the Prius, she got approving glances from the local Berkeley residents because she was driving a Prius. And if you know Jennifer, that drove her batty. She hated that. She's like, I am not driving this to get your approval. I'm driving it because I like the car. But there's absolutely a set of people who will judge you badly if, you drive the car that they don't think you should be driving. And often they think that they have, the right calibration of how much stuff a person needs, and having more stuff than that is somehow wrong. I've said many times people badmouth billionaires, and I think that in the way that our politics and economics are structured right now, there's too much wealth inequality, and I think there's too much power in the hands of a small number of influential people simply because they have money. That's true. But I'm not against the idea of billionaires. I want everyone to be a billionaire. That's what I want. So I'm in favor of the abundance agenda. I am in favor of being on the left-hand side of the political spectrum with encouraging people to do different kinds of things. Some things are bad, for the environment or whatever. And to me, the right thing to do is not to, have moral condemnation of those things, but just to legislate them away, either by making them illegal or, even better, to decrease the incentives to do them by making it easier to do alternatives that are less harmful. So what I'm trying to say is that, my spiritual inclination is absolutely toward an abundance agenda, number one. Number two, I'm entirely sympathetic to the idea that bureaucracies run out of control, right? I've been in universities my whole life. I have plenty of experience with bureaucracies running out of control. And, I lived in LA, where it's just one of the most difficult places to build things, to build new housing or whatever. We had a townhouse, and we thought about building a roof deck on top of the townhouse because we lived in LA and we had no outdoor space whatsoever. It turns out to be essentially impossible to do that because you just can't get the permits in LA. I'm entirely in favor, especially when it comes to housing policy. I'm very much on the YIMBY side, yes, in my backyard, of letting people build a lot of housing. People, I don't know why, but this housing policy is a place where people seem to fail to understand basic economics. If you build more housing, the price of housing will go down. And people think that if you build more housing, the only people that benefit are wealthy developers. That's just not true. People who pay rent benefit because the price of housing for everyone goes down when the supply is bigger. This is a true fact that has been empirically verified over and over and over again. So again, that's point two, is that given the nature of bureaucracies, not just the nature of liberal progressive thought, I am also in favor of making it easier to do good things. However, point three would be, many of these regulations are for a good purpose. Many regulations about energy policy, construction policy, whatever, have very good reasons behind them. So I think you need to be super duper careful, as opposed to what is going on right now, but super duper careful about sifting through the regulations that exist and making sure if you remove them that they didn't have a really strong purpose for being there in the first place. I would like to think that that's possible to do, but rather than just making sweeping statements about abundance, which I'm sure that Ezra Klein and Derek Thompson didn't do, but I don't want to do that. I don't want to make sweeping statements. I think you got to roll up your sleeves and do the nitty-gritty of looking at what regulations there are, what ones can we get rid of to really power charge the economy, which I'm entirely in favor of doing. Ira Howsam says, I'm wondering to what extent, if any, feelings and sensations can be considered evidence or data within the context of Bayesian inference. For instance, when given a choice, a baby or a toddler will tend to choose calorie-rich foods over other foods, seemingly inferring which foods will reduce their risk of starvation, despite not knowing what calories or starvation even are. Well, yeah, I have no trouble whatsoever with feelings and sensations being considered as evidence, but for a good reason. The case of the baby is pretty straightforward. We are biological organisms that grew up through evolutionary time to have certain inclinations and desires for certain reasons. So the fact that we might not know why we have a certain inclination or desire doesn't mean that we shouldn't think that there isn't some reason for it. Ideally, you would think through what those reasons are, because maybe the course of evolutionary history has rendered certain reasons irrelevant now, and you shouldn't be eating as many calories as your intuitions or what is the word? Intuitions, inclinations, instincts make you want to do. Okay, so your rational thought can override the evidence that you get from feelings and sensations, but there's still evidence. It still counts. Kunal Menda says, in the novel Permutation City, Greg Egan explores the idea that consciousness could persist through a series of mental states instantiated on entirely different substrates at arbitrary times and locations, yet still feel like a continuous conscious experience to the observer. Do you find this idea compelling or at least worthy of serious thought? And if so, do you think it's ultimately more compatible with physicalism, or does it gesture toward a view of consciousness that's closer to idealism? Well, I think, compelling or worthy of serious thought, neither one of those is the word I would use. It's possible. It's certainly conceivable. There's nothing violates the laws of physics. I don't think it has anything to do with physicalism versus idealism. I think it's completely compatible with either. Certainly it's compatible with physicalism. But as I think I've said this before, and people like Jeff Lichtman and I have talked about it, it's easy to conjure up these scenarios. People tend to dramatically underestimate the difficulty of pulling it off, of actually copying over an entire brain state into a different substrate and making the new physical substrate more or less functionally equivalent to the old biological one. It's not something we're going to be thinking about anytime soon. I also think that our intuitions break down in these cases. We have been for a very long time here on Earth. Human beings have led basically one life in our biological bodies with our brains doing the thinking. And that is how all of our intuitions have been trained. So from a philosophical point of view, forgetting about consciousness for the second, but people come up with scenarios about duplication machines or teleporter machines and things like that, right? And they say, well, which one is the real you? Are they all you? Things like that. And the problem is that our vocabulary is just not up to the job. We have never had to think about that. That's never how we've been thinking about what it means to be a person who can be exactly duplicated. It's easy to say those science fiction words, but it's very hard to pull it off, so we're just not equipped. And of course, we can use our rational faculties to try to think about it and try to come up with sensible answers, but we're not very good at that, honestly, in the absence of any intuition. I think the same kind of thing is true here with consciousness. Could you, in principle, instantiate in a computer something that had all of the thoughts and perceptions of a person who had been biological for a long time? Sure, in principle, you could do that. Would it then be the person? Who cares? I mean, I think that's a wrong question to ask. It's a different thing. I guess in the real world, you could make an argument, you absolutely could make an argument that a person at every moment is different than the same person the next moment, right? You've had more experiences, you're a little bit older, you feel a little bit differently, you have more memories, whatever. It's a different person. But there is a reason why it is useful to group all of that set of people into one continually existing agent, right? Especially useful for purposes of morality and politics and things like that, as well as personal psychology. So the reasons for that usefulness might become weaker in a world where we could upload to a computer. There's no reason to think that our traditional way of thinking about what it means to be a person continue to be true in this new context. So I think, again, it's super duper possible, but questions about whether or not it's the same person, does that person deserve rights and things like that, are ones that we are really just not very good at thinking about right now. We should think about them, so it's worthy of serious thoughts, even though the prospect is nowhere near imminent, but it will be hard to come up with good, reliable consensus answers to those questions. Marie Roskew says, I've recently listened to an interview with Julian Barber. Julian mentioned, among other things, that laws of thermodynamics were created during the time of steam engines and then hand-put to the laws of physics of the universe by brute force. Also, he said something like the universe was not in a box, and that in an ever-expanding universe, the entropy loses its meaning. There is no increasing entropy. I can't wrap my head around that. Where do you stand on such opinions and theories? There is a certain strain in the physics community that thinks that way, but I think it's a minority strain. You know, it's true that we invented thermodynamics because we had very down-to-earth technological questions about steam engines and boxes of gas. But it's also equally true that we have definitions of entropy that apply to other systems. Like, that was a long time ago. That was, 200 years ago that we started doing that, and we've come a long way since then. I wrote a paper with Aidan Chatwin-Davis about thinking of the cosmic no-hair theorem as a manifestation of the second law of thermodynamics. We have a definition of entropy that we borrowed from a paper written by Raphael Busso and Netta Engelhardt, two former Mindscape guests, which is perfectly good for an expanding universe, for a region of an expanding universe. You have to think about it. You have to put some effort into it. It's not just obvious extensions of what we used to do with boxes of gas or steam engines, but you can do it. So I just don't see what the problem is. It just seems like, well, this is what I learned when I was an undergraduate, therefore it must be the state of the art forever. I don't think that's how it goes. Jackson Race, Raesz, asks a priority question. Have you ever had or plan to have a biblical scholar on the podcast or any related profession such as the cognitive sciences of religion? I feel as if that topic would interest a great portion of your audience. Many of us, such as myself, don't know how to combat the ludicrous power of the Trumpist white Christian nationalist movement. I was myself raised as a Republican Christian, but I can even I can see the madness. I think my third ever guest was Tony Pinn, who was a professor of theology, back in the day. Of course, he is an atheist, but he is an atheist who went to divinity school and grew up actually as a child preacher back in the day. So he's a fascinating character. We've talked about religion on the podcast a couple times. A true biblical scholar to talk about the history of the Bible or certain subsets of the history of the Bible, I think would be great if it were the right person, because I do think that even if I don't believe in the claims of religion, I think that religion has had a huge effect on history and continues to have a huge effect on us. I don't really see myself as learning how to combat anybody's power, but I do think that our culture here in the West, anyway, has been very shaped by our religious traditions. And in other countries, it's been shaped by their religious traditions. So that's a perfectly legitimate subject to talk about. If the right person comes along in the right moment, I would happily do that. Anonymous says, do you see a way we can avoid giving weaponized AI-powered drones autonomy to make decisions about when to strike, i.e., taking humans out of the kill chain, especially considering how effective jamming signals has become? Again, modern warfare and weapon systems are not my expertise, so don't believe anything I say about this. My feeling is the following, that when you have new weaponry or new technology that can be weaponized, you can talk about dialing it back a little bit, right? Like not giving it its full reign. But what if the other people on the other side of the conflict that you're in don't have that compulsion? You're probably going to find yourself changing your mind. I think it's very difficult to predict what people will and will not do. Some people, sometimes we make crazy decisions. I remember talking to a guy who used to work in a laser laboratory. And because of restrictions from the Geneva Convention, I believe it was, you can build a laser that can kill a person. That's okay. Killing people is okay by the laws of laws of war, I suppose. But blinding someone intentionally is not okay. So you can build lasers of certain power levels, but there's a particular band from some low power to some higher power where you're not allowed to build the lasers because they could blind someone without killing them. If the laser were even more powerful enough to kill them, then you can do it. That made a big impression on me, so I might have told you this story before. I suspect that drones, or more generally weapons that do not have humans in the kill chain, as you put it, are going to come. I'm pessimistic about these things. I tend to think that if we invent new technologies that can do harm, we tend to use them. Atomic and nuclear weapons might be the counterexample that you point to, but I will point out we have used them. We did use them on Japan. The United States is the only country that has dropped an atomic weapon in anger. We've been extraordinarily fortunate that they've not been used since then, but it's been less than 100 years. So I'm not too optimistic about all those things. I think that expecting the worst is the prudent thing to do. Ed Said Stuff says, while mathematics is clearly a beautiful, useful language for talking about physics, do the models describe physics itself? To put it another way, are Everett's worlds real? Here's my main question. In order to accept Everett's approach, am I required to accept that useful mathematical models reflect or even are physical reality? The two ideas seem like a package deal. What am I missing? Is there another way to look at it? I think language is a way to talk. I think mathematics, is a language for talking about physics. Physics is physics, okay? The reason why you should accept Everett's worlds is because that's what the physics says. The language that we use to talk about that physics is mathematical, but it doesn't need to be. You could talk about it in words. It's just that you had to be super duper precise, and it's much less helpful than using the math. So I don't think it's right to mix up interesting philosophical questions about mathematical realism or the role of mathematics with the fact that physical theories make predictions. One of the theories of quantum mechanics, if you don't add explicit collapse of the wave function, is that there are multiple worlds. So you can change the theory by getting rid of the worlds, but whether or not you use math or not, that's a change of the theory. Victor Tiffany asks a priority question. On pages 173 to 174 of Something Deeply Hidden, Alice addresses her father's question about whether the many worlds theory violates the conservation of energy. He asks, where does all that stuff come from when you suddenly create a whole new universe? I could measure the energy contained in this world I see around me, and you say it's being duplicated all the time. Her father wants to know why his bowling ball isn't getting lighter with every division of the universe. She had explained that each world got a bit thinner, although its inhabitants can't tell the difference. Addressing her father's bowling ball, she explains, after splitting, it looks like you have two bowling balls, but together they contribute exactly as much to the energy of the wave function as the single bowling ball did before. My question is, if Alice and you are right, why isn't our thinner world something that physicists can detect and measure? The answer is because the physicists are also thinner. In that world, after you measure some spin, the total contribution of the bowling ball that you see is only half of what it used to be, but you doing the seeing are made of various elementary particles that are being also multiplied by that factor of 1/2. When you make a measurement on the mass or energy of a bowling ball, it is relative to your measuring devices doing the measuring, and they're all multiplied by the same factor. So people inside the universes have some giant number outside the universe saying, 1 over square root of 2, 1 over square root of 20, or whatever it is. They have no way of detecting that because they're all within the universe measuring the same things. Now, that's the answer to your question. Let me say as an aside, something I've said certainly on multiple occasions before. This question of energy conservation in quantum mechanics, in many worlds in particular, is the best example I know of something about which there is zero actual scientific controversy, okay? You just have to take my word for it if you don't use the equations are completely unambiguous. There's no problem with energy conservation. That is not a real worry. There are real worries that you can have about many worlds, but this is not a true scientific worry. This is entirely a matter of, do you believe our translation of the equation into words? If you don't believe it, or if you don't sort of feel comfortable with it, then you will struggle with it. But the equations and the theory are entirely unambiguous. There's absolutely no real unanswered questions lurking here. Mikhail Borzowski says, it seems that democracies are often born after wars or other dramatic events when people are relatively united and share a common vision of living better lives. Laws are written from scratch with best intentions to ensure a fair game. As time goes on, I feel like politicians find new loopholes to gain more power, and it's hard to improve and adapt the rules as it's against the interests of those in charge. Does a democracy have an intrinsic need to start from scratch every few hundred years in order to implement major improvements, or can we have long-term stability and an upward trajectory without going through wars? I ask more in the theoretical sense more than with any specific country in mind. I don't know. This is something I have thought of before. I think traditionally in physics, if we think about the physics of democracy angle here, we think that systems, if you let them settle down, kind of reach an equilibrium, and they want to stay that way for a long time. Now, obviously, democracies or countries, nations, states, whatever you want to think about, in the world are not closed systems. They react to things going on in the outside world, so that analogy is not perfectly good. But nevertheless, it seems, I think you're right, that when democracies fail, they are often because of internal reasons, not simply because of external reasons. And it goes both ways, right? Autocracies turn into democracies turn back into autocracies. It makes you wonder whether the idea of a stable equilibrium just doesn't exist in some way. So I've toyed with the idea of the time crystal theory of political stability. If you know what a time crystal is, let's say this. What is a regular crystal? A regular crystal is, you have a bunch of atoms and they're settling into their ground states, right? So the atoms are interacting with each other, but they're cooling off, they're giving off photons, they're lowering their total energy, and they settle into a ground state where it breaks the symmetry of spatial translations because the atoms line up in a particular configuration. And so you get a crystal where here's an atom, there's no atom, here's another atom. Okay, and they sort of come into a lattice structure or something like that. So you get a spontaneous breakdown of the symmetry that is underlying the system that says I can change the position of the system however I want, because now there's some specific positions where the atoms are. So Frank Wilczek and others have played with this idea, former Mindscape guest Frank Wilczek, of this idea of time crystals, which is hypothetically, there's some claims for experimental realization, but I have not really followed that literature very much. Is it possible to imagine a system where the ground state, the lowest energy state, has changes in time, in particular some periodicity? It keeps rocking back and forth. If we think of an ordinary harmonic oscillator or whatever, the lowest energy state classically is no motion at all, right? So it's not actually rocking back and forth. You can make it rock back and forth, but that's not the lowest energy state. Even quantum mechanically, that's true. The state is different, but it's still static, that lowest energy state. Are there physical systems you can imagine where the lowest energy purported equilibrium states are still changing with time, perhaps oscillating back and forth from one phase to another? That's a physics question, but I wonder if that's not a good analogy maybe for thinking about democracy. Maybe when you have for Mikhail, I'm not actually answering your question, but I'm saying that the answer is plausibly yes, that democracy by itself and autocracy by itself are not individually stable because internal pressures build up and you end up switching from one to the other after some period of time. It won't be exactly the same period of time from transition to transition because democracies are complicated and the external world does change and a whole bunch of things, but maybe there is no stable equilibrium even though you just keep changing back and forth between those two possibilities. I truly don't know if that's true or not. It's certainly completely possible to me that a democracy could last for millions of years if you did it right. Again, I'm not saying that's true or would happen, but it's possible to me. So I think we need to understand political science and human psychology a lot better than we do to answer questions like that. Ilya Lvov says, in a recent AMA episode, you contrasted the Heisenberg and Schrodinger formulations of quantum mechanics, as well as commented on Heisenberg's deeply Copenhagen views. I appreciate that the two quantum formulations are mathematically equivalent, but do you believe each of them has a certain ontological oomph? E.g., is it easy or natural to describe many worlds in the Heisenberg language? Why do you personally always cite the Schrodinger equation and not the Heisenberg one? So for folks who don't know, there is a way of thinking about quantum mechanics, which is usually the way that I talk about, and it's called the Schrodinger picture. In that picture, you have two things. You have the quantum state, and you have operators, like you're measuring position, or you're measuring momentum, or spin, or whatever, okay? And the Schrodinger picture says you let the state evolve with time, and the operators are time independent. The actual value that you get for doing an observation will be different because the underlying state is changing, but the thing you're calling the operator is fixed as a function of time. The Heisenberg perspective flips that on its head, and it says that the state doesn't change with time, but the operators do. So you think about x and p, position and momentum, as changing with time as operators, even though the underlying state is the same. As long as everything is okay, in ordinary circumstances, these two perspectives are 100% interchangeable. There might be specific examples where it's tricky. If they're completely mathematically equivalent, my attitude is always that they're equally philosophically or ontologically equivalent. There might be perspectives or ways of thinking that are more natural in one than the other. You know, the idea of the wave function of the universe branching is more natural in the Schrodinger language than the Heisenberg language. David Deutsch, another previous Mindscape guest, did write a paper where he put all of the many worlds interpretation into the Heisenberg picture, so it can be done. It just seems a little bit less natural. Why do I always do that? Yeah, it just is very natural for me to think of states evolving with time. It's accords with my classical training. It accords with how to think about many worlds, but I'm able and willing to think about the Heisenberg language when I need to. Indeed, if you do decoherent histories, which is a formalism that you can think about in quantum mechanics, that is much more naturally phrased in the Heisenberg language, and a paper that I'm writing now does, and so I got to use it, and that's fine. Mark Kumeri says, you often get questions on the Fermi paradox and intelligent life elsewhere in the universe. My initial reaction is always the same. What do you mean elsewhere in the universe? You need to be super duper clear in defining what you mean. Perhaps the probability is far below 1 in our galaxy, but in many worlds, it's trivially 1. But going from our galaxy to the visible universe of about 93 billion light years in diameter surely dramatically increases the probability. And the overall universe, I've read, is very likely at least 250 times larger, or 23 trillion light years in diameter. My naive thinking is that it seems close to 1, the chance of intelligent life elsewhere in our shared space universe. What are your thoughts? I mean, your intuition is right, but I think your numbers, and you need to be careful a little bit. For one thing, who cares what the volume is? Like, most of the volume of the universe is empty space, and that's unlikely to be a hospitable breeding ground for intelligent life. What really matters is maybe the number of planets or stars or galaxies or something like that. There are, roughly speaking, 100 billion or 1 trillion galaxies in our universe, so it is entirely possible, entirely sensible to say that the probability of life in the universe is at least 1 trillion times bigger than the probability of life in our galaxy. I shouldn't say at least. You know, obviously that saturates when the probability gets close to 1. But if the probability of life in our galaxy is small, it gets at least a boost by a factor of 1 trillion. So does that mean that the probability is 1 in the observable universe? Well, that's just asking the question, can I imagine numbers that are greater than 0 and smaller than 1 over 1 trillion? Yeah. I have no problem imagining numbers like that. There's an infinite number of such numbers. If the probability of intelligent life is 10 to the minus 20 in a galaxy, then the probability of it being in the observable universe is still very, very tiny. So yeah, I don't know. I think you actually need to do the work. You can't just do numerology. You really got to think about how life forms, like it or not. That's a fun thing to do anyway, so it's not such a bad position to be in. Nikola Ivanov says, in a couple of podcasts, you explained how the shapes of the acoustic peaks in the power spectrum of the cosmic microwave background show the presence of dark matter. The initial conditions seem to have been that, first, there were fluctuations in the dark matter and the photon baryon plasma to start with, and second, that these fluctuations were initially synchronized, adiabatic. You mentioned in passing that the cosmic inflation hypothesis might explain these features of the initial conditions. Can you please outline how? Sure. Inflation imagines that there is some single field. Actually, I should say, in the simplest inflationary models, there's just one field, but there are multi-field models. But let's just imagine there's one field, okay? If there's just one field doing the inflating, this field has an energy during the inflationary period. It has a very large energy density, and it slowly rolls with time. It's a ball rolling down a hill very gradually, and eventually it sort of comes to a cliff and falls down to the bottom. This moment where the field falls down to the bottom of the cliff, called its potential energy, is known as reheating, because what happens is the energy that was in the field is now turned into particles of the field, and those particles decay. Okay, so you are converting the energy that was into that field to the decay products of the associated particles. And the idea is that the fluctuations that eventually grow into stars and galaxies and whatever come out of fluctuations in the original field. And those fluctuations either exist or don't, right? I mean, they're there uniformly in the field. And then how that field turns into other forms of energy, it turns into photons, into gluons, into quarks and leptons and all that stuff. That's just a matter of the fundamental laws of physics, right? That's just a matter of quantum field theory. In other words, it's not something that changes from place to place. So at the end of inflation, you're left with a certain energy density in the inflaton field that is a certain number, and whatever that number is, it turns uniformly into a mixture of all the other particles in the universe. That's why there's a correlation, there's a synchronization of photons, baryons, and so forth, because they both have a certain probability per inflaton particle of being produced in a decay. And what matters is the original number of inflaton particles, which is some number, whatever it is, at the end of inflation. Natalie Standing says, Max Tegmark speaks about the universe being only mathematical. I was wondering your thoughts on simulation theory. When you consider Benford's law and Fibonacci numbers, do you think that's adding weight to simulation theory? It feels like the world is coded. It does not feel like the world is coded to me. The world is certainly well described by the laws of physics, which are most elegantly explained mathematically, or stated mathematically, I suppose I should say. And that is absolutely a fact. I mean, it's a non-trivial fact. Why are the underlying rules of physics that give rise to the universe we see so elegant and simple and statable in such nice mathematical language? That's a question. But the idea that we are living in a computer simulation is certainly not the only possible answer to that question, or even an especially good answer to that question. My attitude towards simulation theory is always be a good Bayesian about it. If you propose that the world was a simulation, what would you expect it to look like? I wouldn't expect it to look like the world that we live in for all sorts of reasons, mostly empty space, trillion galaxies, things like that. I could be wrong in that expectation, but I need to do that. That's what you need to do as a Bayesian. Tell me what features of the universe are best explained by the simulation hypothesis. It doesn't seem to me to be like you would get a universe like ours, but I could be wrong. Sean Wormuth says, when was the earliest point in the universe when intelligent life could have evolved? How long did it take to create the elements past iron, and were there Earth-like planets in existence then? This is a way of asking if part of the Fermi paradox answer is that we are early. Well, one problem is I don't know what are the conditions under which intelligent life could have evolved. We know the conditions pretty close to the conditions that it did evolve in here on Earth, but maybe it's much more robust than that. I truly don't know, so that's something to keep in mind. If you're particularly looking for Earth-like planets, then indeed it does take some time. The sun is roughly a third-generation star. Because astronomers are kind of backwards, we call the sun a population 1 star. The previous generation is population 2, and the very first generation of stars is population 3, because we always count backwards from ourselves. But it doesn't take that long to go through these generations. You know, the sun will last 10 billion years or whatever. It's halfway through its life cycle. But heavier stars last much shorter periods of time than that. So within a few hundred years, you could easily imagine the first generation of stars having plenty of stars already exploding and spewing heavy elements throughout the universe. It takes time. When you get the second generation of stars is much better at creating heavy elements than the first generation was. So indeed, it makes sense that rocky planets tend to come as orbiting the third generation of stars. But I don't think there's any worry or any reason why you couldn't have had what we think of as third generation stars, 5 billion years after the Big Bang, or maybe 3 billion years after the Big Bang. I truly don't know the numbers, but my strong impression is that there's no reason to think that we are as early as we could be in the universe to have intelligent life like ourselves. Schreiber Bike says, in your interview with Kari Cesarotti on September 16th, 2024, she mentioned that many orders of magnitude between the Planck length and the smallest things we can detect. Are there things going on in that space that you think are important to our reality? Well, the short answer is we have no idea. We haven't detected anything in that space. The second thing is, what do you mean by important to our reality? Do you mean appearing in the laws of physics, which is part of our reality? Or do you mean affecting our everyday lives here in the universe that we see? There's nothing up there that we know about that affects our everyday lives. And I've made plenty of arguments that you can look up online that there aren't going to be any things that we discover in that regime that could affect our everyday lives. The particles that could be up there are much heavier than what we can create in experiments. So either, most likely, if they exist, they're unstable, like the Higgs boson in the top quark, which we can barely create in our laboratories, and therefore they go away very quickly, unimportant to our reality, or they're stable. If they're stable, why haven't we seen them yet? That maybe there is one particle up there, which is the dark matter, right? But that clearly interacts with us very weakly. And it has to be that way. We would have detected any particles that are up there that are stable and easy to produce if they interact with any noticeable strength with the things that we can do here on Earth, and therefore that they would be relevant to our everyday lives. Now, if you just want to know whether there are particles up there, it's an interesting question, and we don't know the answer. Back in the early days in the 1970s, where people were very happy about the success of the electroweak theory, and were trying to unify the electroweak model with the strong interactions to make grand unified theories, the miracle of logarithmic growth of energies predicted that even though all the experiments back then had been done at some number of GeV, some number of billions of electron volts, that this grand unification scale would be up at 10 to the 16 GeV, and that there wouldn't be anything in between the electroweak scale at 100 GeV and the grand unification scale at 10 to the 16 GeV. And this was called the Glasgow Desert, after Sheldon Glasgow, one of the pioneers of grand unification. But we don't know. Grand unification has had a spotty track record. You need to sort of tweak it, since we have better experiments now than we did back in the 70s. It did make one wonderful prediction that the proton would not be stable, but people have looked for that and not found it. The proton is not yet decayed. Maybe it will, but again, you have to make tweaks to the original models to imagine escaping those experimental bounds. So I think not only do we, in principle, not know, but in practice, we truly don't know. I think it is a very open question. John Schoening says, I saw a quote from Einstein recently in which he said that the right side of the Einstein field equations, the stress-energy tensor, was built of low-grain wood as opposed to the other side being made of fine marble. The interpretation given of this was that the equation was mathematically precise but not necessarily physically precise, and that Einstein knew this. Do you think this is an appropriate interpretation of the quote? And if so, what might account for the possible discrepancy with reality? I'm not sure what it means to be mathematically precise but not physically precise. I think I know what Einstein was talking about, but I'm not quite sure about the interpretation you're mentioning. Einstein derived in classical general relativity a field equation for the gravitational field. The gravitational field being, he realized, the metric tensor of spacetime, the field that gives rise to geometry of spacetime. And of course, that field responds to other forms of matter and energy, right? masses, momenta, heat, all those things, pressure, energy density of various sorts. So what he derived was an equation that said, okay, here is how the metric, the gravitational field, responds to whatever forms of energy and momentum you want to give me. I don't know what the right theory of physics is to tell me what the forms of energy and momentum are, but whatever they are, here's how they push gravity around. And the left-hand side of his equation, the one that he liked, was the gravity side. The right-hand side was the matter and energy side that pushes it around. So basically he's saying, I now understand the dynamics of the gravitational field, but I don't understand the dynamics of all the other fields. That's what he was trying to say. And it's true. We still don't understand them. We understand them much better than he did because we have quantum field theory and the standard model and whatever. But still, we're not done figuring out what the universe is made of. That dark matter is an example of something that we don't understand where it comes from. So I don't think it's, a very strong aesthetic difference. Einstein's theory is a theory of gravity, so it's not surprising that it describes gravity better than all the other fields. Lars Kruger asks an astrophysics question. How long does it take for a star in formation, in the process of being formed, in other words, to ignite once the critical mass for fusion is reached? I heard the term light up frequently, but have no clue if this takes a few seconds or if the rate of fusion slowly increases over hundreds of years. Very few things happen in astrophysics over the course of a few seconds. Some things do. When things blow up, a few seconds might be a dramatic time. But even a supernova, when it blows up, takes days to reach peak brightness and then weeks to fade away. So for a star to start lighting up, I don't know exactly the numbers. It's going to depend on details, like when exactly you set the clock to start and things like that. But I would think more in terms of many thousands of years rather than seconds or hundreds of years. 100,000 years would not surprise me as a former astronomer. Alex says, I guess this depends on the field you're working in the university, etc., but I'm wondering, how does an academic year look for a professor like yourself in the United States? Namely, do you do both research and teaching all throughout the year, and then it's up to you to organize yourself as best you can? Or do you have at least nominally dedicated periods for teaching and dedicated periods for research? Asking from the position of an associate professor in France, where all my activities are scrambled all together throughout the year. Yep, they're scrambled all together throughout the year. Teaching is somewhat confined. We have semesters that start generally at the beginning of September, end in May or June. One semester goes from September to New Year's. The other goes from New Year's to May or June, and to May, I suppose I should say. Depends a lot on details. Some universities have a quarter system where they have 3 quarters during the academic year. And then the summer, there's almost no teaching. There might be some teaching, but not generally by people who are professors doing research. So you have moments when you're doing more teaching or less, but you're doing research the whole way through, hopefully. Obviously, if you try to pack all the teaching you can do into one semester so you have the other semester free to do research in or to travel or whatever, then that packed semester is going to be harder to do research in. The amount of teaching that people do depends a lot on where they are. You do a lot less teaching as a tenured faculty member at Harvard than you would at a state school or a small liberal arts college or a community college or whatever, which are more teaching focused perhaps. But generally, no, it's not like here is your teaching period, here is your research period. And thank goodness, because research doesn't work that way. I think that, research is something that comes and goes as it wants to come and go. If you were tied to only doing it during certain parts of the year, at least as a scientist, that would be very hard to pull off. Wonder asks a one-word question. This is the shortest question we've ever had in the history of the Mindscape podcast. And the question is, Puck? He or she is asking about Puck, our little stray cat. So I'm looking around. Where is Puck right now? Oh, there he is. He's on his cat tower, from which you might infer that Puck is still with us. And indeed, I will absolutely promise to give you an update if Puck ever moves on to another home. He came close. In fact, we had a candidate, we had a family who wanted to adopt him, and they did. They took him for about a week, and then they realized they were just not cat people. They had been dog people, and they moved from Arizona to Baltimore. and their dog died around the same time, so they had a smaller yard, and they thought maybe a cat would be more appropriate. But then they were shocked at like, oh, this cat runs around in the middle of the night. This cat climbs on the furniture. Other things that cat people are not shocked by. So they gave him back, sadly. So that's very disappointing to us, but we are still, we love the little bugger so much, the little puckster. And it's on the one hand good to have him back. On the other hand, he needs to find a permanent home. We're not going to let him outside again as an outdoor cat. It's too dangerous. It's an urban neighborhood. It would just not be fair to him. And he has no desire to go outside that he's ever expressed. But he loves us. He's much more reliable. If you come into the room with Puck and sit down, he's on your lap like that. He wants to be on your lap. He wants to get his scratches. He wants to be with his people. Much more reliable than Ariel and Caliban, which just take us for granted, honestly. So sometimes if you just want some kitty time, it's good to come up and bond with the puckster. But we don't have the time or the bandwidth to do that as much as he deserves. He deserves a full-time family. And it's a tricky thing because he deserves people. The perfect Puck family will be people who are cat people but don't have a cat, and also don't have a dog or small children or other things that a stray cat might not get along with very well, and also spend a lot of time at home so they can give Puck the attention he deserves. So we're still looking for that. If you know anyone, not only just in Baltimore, but within a couple-hour drive from Baltimore, who might be the perfect family for Puck, please let us know. We're going to keep trying. Dave Whip says, congratulations on the most recent recipients of the Mindscape Big Picture Scholarship. My question is, given the recent changes to government funding of science, what are your thoughts on using crowdsourcing more broadly to fund postgrad and beyond? If a new steady state could be achieved that provided similar level funding from private donations to replace the taxpayer, is there any fundamental reason to prefer public funding over private? I think the fundamental reason to prefer public funding over private is that you're not going to reach a similar level of funding from private donations. This is literally the purpose of having a governmental organization, because there are certain things that the society as a whole needs and wants to do that shouldn't be burdened on individuals because they're feeling more generous than others. They're social goods, whether it's taking out the garbage or building up national defense or giving scholarships to people who can't afford to go to college. These are things that are social goods that society should take care of. And I have not given up on the idea of living in a well-functioning society where people pay taxes, the government distributes money equitably. We will always disagree on what that means to distribute it correctly, but that's okay. That's a conversation that we should all have. Theo Lind says, optical lenses used in action sports like cycling and skiing are rarely polarized because polarization reduces the amount of visual information available to the athlete. Instead, colored lenses are selected to strategically enhance sight. Can hue filters be considered as a practical ultraviolet cutoffs in an applied effective field theory? So I'm not sure exactly what you mean by that. The idea of an ultraviolet cutoff in effective field theory is we think about an infrared theory, a low-energy effective theory that describes particles and energies below a certain value called the ultraviolet cutoff, and we don't directly consider things going on above that cutoff. So in the sense that there are effects from higher energy particles and things like that, like there was a contribution of the Higgs boson to the total interaction cross-section between two electrons long before we directly discovered the Higgs boson. You can calculate what it is. It's very, very tiny, so you don't know exactly what the Higgs boson is doing, but in principle it's there. But the point of effective field theory is whatever those contributions are, they can be summarized in a small number of terms, a small number of interaction possibilities that are only referring to the low energy infrared parts of the theory. Now, if what you're asking is, instead of simply a single cutoff that says, ignore the ultraviolet parts, only keep the infrared parts, could you, have a cutoff band where either you said, ignore everything between this energy and that energy, or you said, ignore everything below this energy, but not everything above, keep everything below this energy, but don't ignore everything above that energy. Ignore everything above a higher energy. So I'm still not saying that correctly. Keep everything below a certain energy, ignore everything above that energy up to some even higher energy, and then start keeping things above. Okay, that would be an example, I guess, of a cutoff band rather than a cutoff sharp plateau. That doesn't work because the ultraviolet stuff, the higher energy stuff that you're trying to put back in, would decay into stuff that is in your cutoff region. And so it's not trivial to say that I can specifically ignore high energy things and still get a sensible, complete, self-contained theory of low energy things. It happens to be true in quantum field theory for reasons having to do with how quantum field theory is constructed, but you can't be arbitrary or clever about the different kinds of things that you include or don't include, okay? You just have to say, here's a cutoff, and I'm going to exclude everything above that cutoff. If you try to be more subtle or sophisticated about it, you're going to end up not getting a sensible, internally consistent low-energy theory. Tim Converse says, in computer science grad school, I took courses in what the CS theorists called complexity theory, which is about classifying problems by how the resources needed to solve them, like time and memory, grow with the size of the input. The P versus NP question is the most famous problem in this kind of complexity theory. When I first heard about complexity theory as practiced at, for example, the Santa Fe Institute, I thought it might have something to do with CS complexity theory, but it looks like it's just an overloaded term or a name clash. Do you think that's right? CS complexity theory is also pretty tightly defined as an area. Describe a problem and I can tell you whether it's a complexity theory problem. Do you think that there is any similarly tight characterization of the Santa Fe style complexity theory where researchers would agree on what problems fall within that area and which don't? You're absolutely right that the term is overloaded. We talked about CS complexity theory in the podcast with Scott Aronson some time ago. And I think we mentioned it on other occasions, but it is a different thing than SFI type complexity theory. And the overloading doesn't stop there. In quantum mechanics, in quantum information theory, there's a thing called the complexity of a quantum state that is neither SFI type complexity nor CS theory type complexity. It has to do with how many gates you need to apply to an initial fiducial state to make the quantum state you're interested in. This turns out to be relevant to black holes. Leonard Susskind, who was previously on the podcast, has worked on this, etc. So there's lots of, complexity is a very robust, very useful term in all sorts of contexts, so you shouldn't be surprised that it gets overloaded a little bit. You're also correct to say that the CS-style complexity theory is super well defined. We call it computer science complexity theory, but these are kind of mathematicians. They're applied mathematicians, honestly, and they're good at defining things crisply and rigorously, and they've done a good job at that. Whereas at Santa Fe, you're trying to deal with the idea of a complex adaptive system, right? Which could be anything from a human brain to a tree to the internet to the economy to a bacterium. There's many, many things that could count as that, and therefore the set of problems you're interested in is much less well defined. I think that's okay. I think it's an ongoing question. What are the useful insights that we can get by thinking of complex systems, not simply as trees or bacteria or economies or whatever? We might get some shared insights, and I think we have gotten shared insights. So that's good, even though we don't have the once and for all crisp, clear definition. Gordell says, over the years, I've seen you respond to people curious about pursuing physics at a research level, often later in life, after a career in another domain, or even post-retirement. They're not looking for a casual hobby. They want to seriously engage with the work the way one might take up flying or piano with real commitment. Your advice is always thoughtful, but understandably tends to touch on employability, how competitive academic positions are, and the limited opportunities akin to making it as a professional athlete. But what if employment weren't a factor? What would you say to someone who's willing to do the hard work, study deeply, contribute meaningfully, but has no need to earn income or compete for institutional support? That's a great question. I think it's a great aspiration for people to have. I strongly encourage people who are oriented that way and don't need the money, don't need the income, to think about doing that if that's what they want to do. But, let me nevertheless throw a little cold water on the possibility, not because I want to discourage anyone, but because I wanted everyone who is thinking along these lines to go into it with their eyes open, okay? It's not just about getting a job. It's about doing the scientific research well, okay? If you're not interested in getting a job, then your motivations might be different than other people's motivations. Getting a job is kind of like tawdry and down to earth, et cetera, and can absolutely, I will not deny, lead people to do things for careerist reasons rather than for the pure love of knowledge. But it also focuses the attention a little bit. You have to do things that other people care about. You can't just, twiddle your thumbs doing things that you have invented and no one else thinks is interesting at all, because that was not going to get you a job. Whereas if you are completely independent, you are free to do literally whatever you want, which sounds good, but individual people are not as smart as people who are trying to engage with collectives, okay? The desire to be understood, to make progress, to understand what other people are doing, to have people realize new knowledge because you have come up with it and you have communicated it to them. All of these are good motivations. So whether or not you get a job or not, I think that the tricky thing to get right would be becoming part of the scientific community. I think that's crucially important. In math, it is just barely possible to make truly deep contributions almost in complete isolation. Kind of for reasons related to what we were just talking about, mathematical questions can be so well defined that someone can define the question, you can individually go off and hide away for years and struggle to solve it and come back with a solution. That has been done in mathematics. Science is much, much harder to do that. There are a lot of papers being written, a lot of science being done, a lot of communication goes on in the form of talks and informal emails and conferences and things like that. It is much more a collective enterprise. And you could do that. There are people who do it. Look, Julian Barber, who's mentioned before, is someone who doesn't have a job as a professional physicist. He, for most of his career, I believe, he supported himself by translating physics papers from Russian to English, and perhaps vice versa, I don't know. But that was his income, and then he separately does his science. And, that's great. You can do it. It can be done. But Julian, also goes to conferences and gives seminars and participates in the community. I think that that's the thing that you would have to sort of truly dedicate yourself to doing. And if you want to do that, then great. Then you can do it. But it's not just a matter of having a job. It's a member of being part of this collective enterprise. Franketh Rag-Kurno says, I'm currently reading From Eternity to Here, available in all good bookshops, and I have a question about light cones. Do light cones intersect? That is, could an event that is currently outside of my light cone, say at Proxima Centauri, interact with an event in my light cone in 4 years' time, and given an infinite timeline, would all light cones in a finite space ultimately overlap in both the past and future? So the short answer is yes, light cones overlap all the time. Whenever you see two things coming from different directions, literally in the room you're in right now. Look to the left, see something. Look to the right, see something, even if it's just the wall. You are at the intersection of two light cones. That's why you're able to see more than one thing at a moment in time. So yes, something from Proxima Centauri can happen, and someday you can observe it, right? That's an intersection of a light cone. But the reason why it's an interesting question is the last little bit. Given an infinite timeline, would all light cones in a finite space ultimately overlap? You might think so, but that's because your intuition is not trained in the expanding universe. In general relativity, where space can expand, and indeed in our real universe where it is expanding, it is possible for two objects that if they were stationary, if the universe were not expanding, their future light cones would intersect, but they are actually moving apart from each other, and the expansion of the universe is so fast that they move apart faster and faster, so that in fact light from one will never be able to intersect the light cone of the other one. And this is literally what you get in a cosmological horizon, okay? It would also happen inside a black hole. If you throw something into a black hole, in the classical black hole, forget about evaporating black holes and Stephen Hawking and things like that, but classically, the light cones that go from the future of something that is already inside the black hole just hit the singularity. They never come out, so they never intersect light cones outside. But it also happens kind of in a more fun, non-trivial way in an expanding universe if the universe keeps expanding fast enough, like it would if we have a cosmological constant pushing things apart. Sandro Stuckey says, the episode with Christoph Koch was a wild ride in a good way. There's one thing I don't understand, which is his argument that simulated minds cannot be conscious because they don't have causal power. He gives examples of simulating black holes or rain and says they won't suck you in or get you wet, which I buy. But simulating a brain seems different because you could actually hook it up to actuators and sensors and then it can affect the world. LLMs do that already, and so do self-driving cars. Does that mean LLMs and self-driving cars are conscious, but a disconnected simulation of a brain cannot be, even if the latter perfectly simulates each neuron? Am I missing something? Do you understand his argument? Well, I think I understand the argument, but I also think I don't agree with it, which maybe means I don't understand it. That's certainly possible. Having a simulated brain in a perfectly simulated, I shouldn't say perfectly, but in a completely simulated environment would be subject to the argument that Christoph is trying to make there. It's not affecting the world, it's just affecting other simulated things, right? That kind of is the good analogy to simulating a black hole or a hurricane or something like that. But like you say, you can simulate a brain and have it interact with the world. Put it in a robot. It's not that hard to imagine. And then why wouldn't it be, in principle, why couldn't it have the capacity to be conscious in exactly the same way like a biological brain would be? I see no reason why it wouldn't. So I'm on your side, I guess. But I feel a little guilty because you should ask him. I mean, maybe he won't, answer, but I always feel a little bit weird trying to explain the arguments of the people who are guests on the podcast. Sometimes I try to do it, but you shouldn't take my word for that as too definitive. Let's put it that way. Okay, we're at our final question, and it comes from David Witch, or Wyke, W-Y-C-H. Imagine the following ancient society. Thousands of scribes collect data on absolutely everything they possibly can and present these mountains of data to an oracle, of whom they can ask questions. If a well-formed question, for which the data is sufficient, if asked a well-formed question, the oracle never seems to err. In other words, it's always correct. However, the society can't know ahead of time whether the question will be adequate or the data collected is sufficient. The oracle never refuses to answer the question. The oracle also never produces how she knows the answer. She just gives it. In fact, the society is developed over time such that they don't even think to ask how she knows. They just accept the answers. Through the oracle, the society has become very advanced but strange, e.g., they transport water down from a mountain lake in enormous sophisticated metal carts filled with stacks of cuboid sacks made out of sheepskin. They had never thought to ask if there was a more efficient way to transport water down the mountain. Can this society be said to be doing science? Do they actually understand the world through her? In the long run, would the society be better off abandoning the oracle and starting over, or better off keeping the oracle and advancing with only her as their guide? I'm not sure if David has in mind any analogy with AI or anything like that, but I'm not going to try to read that into the question. Indeed, this thought experiment is something that I have more or less equivalently talked about in various places. I can't remember exactly where now, but sometimes I talk about it in response to a statement that was made by Steven Weinberg, one of our greatest physicists of the 20th century, but he's made a couple of statements that I just disagree with. And one is in his famous textbook on general relativity and cosmology called Gravitation and Cosmology. He is trying to argue in favor of a perspective on how you should think about general relativity. And it's kind of a particle physics perspective or a field theorist perspective. And there are some people who still have this perspective. And it's anti-geometric. In other words, he says, look, there's a gravitational field, the metric tensor, and it has some dynamics, and those obey differential equations, and I should solve those differential equations. That's what I should do. And I should use those solutions to predict the outcomes of experiments. And he says very explicitly, I don't care whether you talk about space-time as having a geometry or curvature or whatever. All that matters is the positions of dots on photographic plates. Thinking, of course, of, astronomical observations of the location of Mercury or gravitational lensing or whatever. And I think that this attitude is deeply wrong-headed, honestly. And I say that with utmost humility because Steven Weinberg is way smarter than I will ever be. But it's not right because the way that we think about these things, the sort of metaphors and intuitions and images that we use to think about our scientific theories matter enormously to improving those scientific theories, to going beyond them. That it's those bits that really count as understanding. Another time that I wrote about this was in response to Chris Anderson, who I guess was the editor of Wired magazine for a while. He wrote an article about, and this is 20 years ago, but he was prefiguring the big data era, right? It wasn't necessarily about AI, but it was already clear that there was a certain way you could do science, which is just curve fitting to big data, okay? Rather than trying to come up with the theory, the model or whatever, you just have enough data, you fit the data by some curve fitting procedure, and then you use that to make new predictions. And he says, that's the future of science. That's what we're going to do. And I wrote a response piece saying, oh my God, I hope not. That's certainly not what we think of as science. And the example I gave was, look, that's what Kepler did. Kepler, in understanding the motions of planets through the sky, realized that you can do a much better job by imagining they move on ellipses rather than moving on circles with epicycles, okay? And that was great. That was a forward advance in science. Kepler's laws, the planets move on ellipses with certain speeds, etc. But very soon thereafter, Isaac Newton came along and explained why the planets move on ellipses. It's because they are subject to an inverse square law of gravitation. That's better. The curve fitting is good. It's a step, but it's not understanding. It's not knowledge of the underlying mechanism. So anyway, it's the very last question here. So it's a long answer to say that this oracle idea, I've literally, said, what if we had a black box that could answer any possible science question that we asked, but only of the form if these conditions obtained, what would happen next, right? So it doesn't tell you the laws of physics. It just tells you the outcomes of experiments. That is not scientific understanding. It's a replacement for experiments. It would be great to have such an oracle because you could say, if I smash particles together with Planck scale energies, what would come out, right? That would be very, very useful. It would be cheaper than building a particle accelerator. But it's not the same as the understanding we get from a good theory. So would society be better off by abandoning the oracle and starting over? I don't see why you would want to do that. You could have the oracle and use it in various useful ways, but I wouldn't think of the oracle as a replacement for true scientific understanding. A true scientific understanding is exactly that kind of compression we were talking about before in the context of the question about Jeff Lichtman and the brain. Jeff wanted to argue you can't completely compress the brain. The brain is just a brain. It's sui generis. But of course there are features of the brain that are highly compressible, that I can understand certain features of the brain without understanding 86 billion neurons hooked up together, okay? And that's what science is. It's looking for those patterns, those rules, those things that we can compress down to pithy mottos that we call the laws of nature. And we're not going to stop doing that, and we shouldn't stop doing that because that's what science is all about. I'm going to choose to believe optimistically that science is going to march forward for quite a while yet to come. Thanks, as always, to everyone who supports the Mindscape podcast and pays for these AMAs, etc. You're a great audience. It's a pleasure to spend some time just thinking about these wonderful questions you ask, and I'll talk to you next time.